Hello everyone, welcome back to General Chemistry. Today's topic is going to be the equilibrium of acids and bases. Let's get started. Okay, equilibrium of acids and bases. So before we can talk about the equilibrium of acids and bases, we need to look over the definitions of acids and bases. We need to look over our definitions of acids and bases. I think I provided a definition back in video number 4 maybe, which we'll be reviewing again right here. So 3 definitions for acids and bases that are in common use. I don't know if there's a 4th one or a 5th one and beyond. I only know of 3. And those 3 definitions are the Arrhenius definition. There's a name that we've been hearing a lot lately. There's the Bronsted-Lowry definition, which is what we're going to be sticking with for the rest of the course. And there's the Lewis definition of acids and bases, which isn't really going to be used except in video number 20, and video number 20 is going to be optional for a lot of you guys. So many of you probably won't use the Lewis definition at all until you get to organic chemistry. But yeah, 3 definitions. So each definition basically just allows more things to count as acids and bases. That's basically how these progress. So Arrhenius is the strictest definition, where an acid is anything in aqueous solution that increases the concentration of the hydrogen ion. Anything that increases the concentration of the hydrogen ion. And a base is, again, anything in aqueous solution that increases the hydroxide concentration. So an example of an Arrhenius acid would be something like, say, hydrofluoric acid in aqueous form. If you put it in water, then it will dissociate into hydrogen ion and fluoride ion. And yes, I'm using equilibrium arrows because a lot of acids and bases do not dissociate completely. They stop after reaching an equilibrium. An example of an Arrhenius base is aqueous ammonia. So let's see. I guess it would react directly with water, taking off a hydrogen, forming ammonium and hydroxide ion. So yeah, it produces hydroxide ion, therefore it can increase the concentration of hydroxide ion. And let's see, those are aqueous, that's a liquid. Okay, good to go. So, Arrhenius doesn't cover a case like, say, HCl gas. If you have HCl gas and you add it to water, then you should get, well, I guess there's 2 different ways of writing this. So I'll write it both ways. So you can put HCl gas in water and it'll dissociate into H plus and Cl minus, or it can react with the water directly and form what's known as the hydronium ion, H3O plus and Cl minus. And I just realized I didn't leave enough space to write down the definition of Bronsted-Lowry acids and bases. Oh well, we can always do that on another sheet if need be. So yeah, HCl gas would not count as an acid under the Arrhenius definition. However, it does count under the Bronsted-Lowry definition of an acid. So under the Bronsted-Lowry definition, an acid is any substance capable of donating a proton. Proton donors. While a base is a proton acceptor. A base will take protons away from some other compound. It's a proton acceptor. What do protons have to do with this? Well, think about the hydrogen ion. Think about the hydrogen ion, H+. What is that? Well, neutral hydrogen atoms are just a proton with one electron going around them. And to make the hydrogen ion, you remove that electron, which just leaves you with a proton with nothing surrounding it. That's what the hydrogen ion is. And of course, depending on which isotope of hydrogen, you could have some neutrons along with it, but most hydrogen on planet Earth is going to be of the first type with just one proton and no neutrons. So yeah, it's a proton. It's a definition that's based on the ability to donate or accept hydrogen ions, also known as protons. So under the Bronsted-Lowry definition, HCl gas is still an acid because it can give hydrogen, it can give a proton to something else. And in this case, if you look at the top reaction I wrote, it gives its proton to the water molecule, causing it to form hydronium. And this top version of the reaction is typically how we're going to write reactions involving acids and bases from now on. From now on, we will typically include water as a reactant. We will typically include water on the reactant side of the equation. Okay. Also, by that definition, the water here is acting as a base. The water is acting as a base because it accepts a proton. It receives a hydrogen ion from HCl. So you actually have both types of substances in this reaction. We are not going to write our equations like this very often anymore. We might still do it sometimes just to save time, but essentially we're going to treat the hydrogen ion and the hydronium ion as being the same thing. We're going to treat hydrogen and hydronium as being the same. So yeah, that's your Bronsted-Lowry definition. So everything that counted under the Arrhenius definition still counts under the Bronsted-Lowry definition. Anything that increases the hydrogen concentration must have donated hydrogen, so whatever counted as an acid under the Arrhenius definition is still a Bronsted-Lowry acid as well. Same thing goes for bases. Bases increase the hydroxide concentration. Well, hydroxide can act as a receiver of hydrogen ions, a receiver of protons. So again, anything that counted as a base under the Arrhenius definition is still a base under the Bronsted-Lowry definition. And yeah, then we've got the Lewis definition, which basically opens Pandora's box and makes almost everything an acid or a base. So under the Lewis definition, an acid is an electron pair acceptor. Electron pair acceptor. While a base is an electron pair donor. Electron pair donor. So an example, pretty much the only example that I think of whenever I do this chapter, but I know there are plenty of other examples that you see in organic chemistry. What was it? So we've got, it was BF3. I'm not going to draw the lone pairs just to save time. BF3 reacting with NH3. I guess I'll draw this lone pair because it's important. To form the following compound. So it would be the 3 fluorines. Again, not going to draw the lone pairs for the fluorines to save time. And then N, and then the 3 H's. Okay, under the Lewis definition, this would be an acid. This would be an acid because it accepts a lone pair of electrons from the nitrogen in ammonia. The lone pair from nitrogen forms a bond with the boron atom, forming this molecule overall. And since NH3 is donating electrons, this would be called a Lewis base. So, anything that counted as an acid under the Bronsted-Lowry definition is still going to be an acid under the Lewis definition, because anything that is a proton donor is basically receiving electrons. It's accepting electrons. If you look at HCl gas, for example, you can think of the HCl as receiving one of the lone pairs off of water, and one of the lone pairs from water forms a bond with the donated hydrogen to form H3O+. Maybe it'll be easier to see if we look at the structures. So I'll draw HCl backwards like this, and H2O will look like that. So essentially you've got your lone pair over here, forms a bond with the hydrogen, allowing the bonding pair between hydrogen and chlorine to just become a lone pair on the chlorine. So I guess I'll draw the lone pairs on chlorine for this one. And the end result is, and I don't know if I can even fit this in, but chlorine ends up on its own with 4 lone pairs. And hydronium, where am I going to draw it? I guess I'll try to fit it in here. Hydronium, you've got 1, 2, 3 hydrogens. I don't even know if you can read that. 3 hydrogens and a lone pair on the oxygen. And I guess I should put that in brackets and put a positive sign on it, but there's really not enough space. So yeah, anything that's a proton donor basically functions as an electron pair acceptor, and the reverse is also true. Anything that acts as a proton acceptor is essentially an electron pair donor. The water accepted a hydrogen from HCl. It also donated a lone pair to make the bond with that proton. So, yeah, Lewis doesn't overwrite any of the acids and bases that counted under Arrhenius or Bronsted-Lowry. It just includes things that didn't count under Bronsted-Lowry. BF3, for example, boron trifluoride, would not have counted as an acid under Bronsted-Lowry or Arrhenius. It doesn't count under Bronsted-Lowry because, well, it doesn't have any protons to donate. And it's pretty obvious why it doesn't count under Arrhenius. Same reason. It doesn't have any hydrogens. It doesn't have any way of producing hydrogens, so it can't increase the hydrogen concentration. Okay, let's focus more on Bronsted-Lowry for a minute. Let's focus a little bit more on Bronsted-Lowry. How about I'll do HF aqueous reacts with water to form hydronium and the fluoride ion. Okay, so under the Bronsted-Lowry and also the Lewis definitions, the only way that something can function as an acid is for something else to function as a base at the same time, and vice versa. So you do have to have a pair. You do have to have a reaction between an acid and a base in order to have Bronsted-Lowry or Lewis acids or bases. If something is going to be donating protons, you can't donate if there's no one to accept the protons. Same thing with electron pairs. You can't have an electron pair acceptor without an electron pair donor, or vice versa. So there's always going to be one acid and one base in any reaction involving a Bronsted-Lowry acid or base. So we already saw this before. In this case, we've got HF functioning as an acid, and we've got H2O functioning as a base. HF is giving us protons. It's giving protons to water. Water is receiving them, so it's the base. And this gives rise to the concept of a conjugate acid and base. So if I write this reaction backwards, which I totally can, if I write this reaction backwards, then it is possible for hydronium to react with the fluoride ion. To form hydrofluoric acid and water. Whoops. And water. This is possible. Well, in this case, the hydronium is acting as an acid. It's giving one of its hydrogens to the fluoride ion. So the fluoride, being a receiver of protons, is acting as a base. So hydronium is an acid. This is what we would call the conjugate acid. Usually we'll just abbreviate it C acid for, the sake of brevity. That feels redundant. I mean, that's what an abbreviation is. I'm rambling. And a conjugate base, that's what fluoride is. So, yeah. anything that used to be a base in the reactants of the forward reaction will turn into an acid. It'll function as an acid in the reverse reaction. If water accepts a proton, it becomes hydronium, which is now capable of donating protons. So, yeah, base turns into its conjugate acid, and acid turns into its conjugate base. And I guess I'll spell out the word conjugate in case you care about the spelling. I mean, you're going to see the word often enough, but yeah. So, how can I tell if two things are conjugates of each other? Really simple. The difference between them is going to be one hydrogen. If it's one hydrogen less, then it's the conjugate base. If it's one hydrogen more than the original, then it is the conjugate acid. Really, really easy to tell. Nothing that you should be getting tripped up over. Also, the term conjugate is relative. The term conjugate is relative because there's no reason why this has to be the forward reaction. I can, like I've done down here, I can write the reaction in reverse. So it's not like, as the word conjugate is kind of like the word twin, is basically what I'm trying to say. It's kind of like the word twin. If I say Adam and John are twins, saying that Adam is John's twin is the same as saying that John is Adam's twin. There isn't like a prime twin, so to speak. So, being the conjugate acid or base does not imply superiority or inferiority. The word conjugate is just there to emphasize that it's related to something else in the reaction. But usually we will use the word conjugate for whatever we arbitrarily put on the right side of the equation, and we don't use the word conjugate for what's on the left side of the equation. Okay, so that's conjugate acid-base pairs. Let me see. So I guess now we can start digging into the concept of pH. You've probably heard about it in your class before. I don't think I've ever mentioned pH in any previous video. Or maybe I might have. I don't remember. But I feel like I haven't. So let's go ahead and talk about pH. pH and pOH, for that matter. These are measures of acidity or basicity. Measures of acidity or basicity. And because basicity is a word that some people have trouble pronouncing and doesn't roll off the tongue all that easily, you can also call it alkalinity. Alkalinity. So yeah, basicity, alkalinity, same thing. If we say that something is basic, or if we say that something is alkaline, same meaning, just different words. I imagine alkaline is the word that homeopathic medicine people use. I don't know what the term for those people is, so I'm just going to call them homeopathic medicine people. And as for whether or not I think homeopathic medicine works, that's a political question, which is best left for a different kind of video. Okay, so pH and pOH. They allow us to measure acid or base strength. So how do they work? Really, really simple. pH is equal to the negative logarithm of the hydrogen concentration in some sort of equilibrium mixture. Or maybe it's not an equilibrium mixture, maybe it's just a one-way reaction, but it's the negative log of the hydrogen concentration in some sort of solution. Or the negative log of the hydronium concentration in the solution. We're going to be treating hydrogen ion and hydronium ion as being the exact same thing. POH follows some similar logic. It's the negative log of the hydroxide concentration in a solution. I hope you remember your logarithms. I mean, we've used logarithms in video number 12, I think. Did we use it in the previous video? I don't think we did. But yeah, we did use it in video number 12. We used, I think, the natural log for some example. So if you still haven't reviewed your logarithms and how they work, now is the time. Well, actually the time was 2 videos ago, but I digress. So if I have, let's say, a 1 molar hydrochloric acid solution, if I have a 1 molar HCl solution, then HCl happens to be one of those acids that completely dissociates, so single arrow, not equilibrium arrows. If I have 1 molar to start with, all of it disappears and turns into 1 molar of hydrogen ion plus 1 molar of chloride ion. And so you would have a solution that has a concentration of hydrogen ion at 1 molar, negative log of 1 molar. This is log base 10, by the way. That's what it is by default on your calculator. A negative log base 10 of 1.0, which I guess is going to be 0. Okay, maybe that's not the best example. But yeah, that's a pH of 0, which is actually very, very acidic. The higher the concentration of hydrogen ion, the lower the pH value. So pH, I guess, will have it range from, it doesn't have to stop at 0, but let's have it range from 0 to 14. From 0 to 14. So the closer you are to 0, the more acidic. The closer you are to 14, the more basic. And at room temperature, if the pH is 7, then you have a solution that's neutral, like plain old water. I guess you can't really see that 7 very well. I'll write it down here. At a pH of 7, at room temperature, you end up with a neutral solution. So why is a pH of 7 considered neutral? Let's take a look at a special chemical equation known as the auto-ionization of water. So if you look at the screen, you can see 2 water molecules. One of them gives a hydrogen ion to another. So one of them acts as an acid and the other acts as a base. And of course, the receiving water becomes the conjugate acid and the donating water becomes the hydroxide ion, which is the conjugate base in this case. So yeah, that's the auto-ionization of water, and as you can tell by the equilibrium arrows, it doesn't go all the way to completion. At room temperature, the equilibrium constant for this process is a special value known as Kw, and its value is 1.0 times 10 to the negative 14. So we have Kw. Actually, let me do this on a new sheet. I want to actually write the reaction so we can look at it. Kw is equal to 1.0 times 10 to the negative 14 at room temperature. I guess I'll write it down here in parentheses, at 25 degrees Celsius. So that's H2O with itself. I'll just write it as 2H2O liquid, forming hydronium ion plus hydroxide ion. Okay, if I write the equilibrium expression for this, assuming equilibrium is reached, so the water doesn't count, of course, but you can assume you have an excess amount of it, and, some amount of it, x, is going to be lost. These, let's say they start at 0, and they both increase by x. I'm not writing out a full ice table here, but I hope you can tell what I'm doing. So at equilibrium, we would have Kw equals the final concentration of hydronium times the final concentration of hydroxide, which in this case 0 plus x times 0 plus x, that's equal to x squared. So if x squared is 1.0 times 10 to the negative 14, then if you take the square root on both sides, you get x equals 1.0 times 10 to the negative 7. And if I take that's equal to what? 0 plus x. X is the final concentration of hydronium and the final concentration of hydroxide in just ordinary water. So we can say that H3O plus concentration equals 1.0 times 10 to the negative 7, and so does the hydroxide concentration for that matter. So whether you calculate the pH or the pOH, negative log of 1.0 times 10 to the negative 7, I would hope you could tell without a calculator that this is going to be equal to exactly 7. So the pH is going to be 7, and so is the pOH when you've just got regular neutral water at room temperature. And yeah, that's why a pH of 7 is considered neutral. That's why 7 is the neutral number, but this is only true at 25 degrees Celsius. At higher temperatures, neutral is going to be at a different number. And same for lower temperatures for that matter. I think the more the temperature goes up, the higher the value of Kw, which would mean that the neutral pH would be lower than 7 at higher temperatures and greater than 7 at lower temperatures. We'll probably see an example involving that at some point when we look at problems. Let's see. Oh, and let me wall that off. So the other thing that we can take away from this is that when the concentration of hydronium goes up, the concentration of hydroxide has to go down and vice versa. After all, their product has to be Kw, which is a constant at room temperature 1.0 times 10 to the negative 14. So if I have this 1 molar HCl solution that I used as my example, we got a pH of 0. We got a pH equal to 0. What about the pOH? There is no hydroxide in this reaction, so how do we figure out the concentration of hydroxide? We just take advantage of Kw. Assuming this happened at room temperature, and I guess I'll do it on this sheet. Assuming this occurred at room temperature, then Kw, 1.0 times 10 to the negative 14, would have to be equal to the hydrogen or hydronium concentration, so that's going to be 1.0, times the hydroxide concentration. So in other words, the hydroxide concentration equals Kw divided by the hydrogen or hydronium concentration. And the hydrogen or hydronium concentration is going to be Kw divided by the hydroxide concentration. So if you have the concentration of one but not the other, Kw divided by the one you have gives you the concentration of the one you don't have. Okay, so I guess that just makes the concentration of hydroxide really, really small, not a surprise there. 1.0 times 10 to the negative 14. And if I calculate the pOH, it's going to be the negative log of 1.0 times 10 to the negative 14, which is 14. Ooh. Okay, what if I tried something different? What if I tried a solution, and I'll just make something up here. What if we had a solution where the hydronium concentration was equal to 1.0 times 10 to the negative 5 molar. What is the pH and what's the pOH? pH is going to be negative log of the hydronium concentration. Negative log base 10 of 1.0 times 10 to the negative 5 is just going to be 5. Well, it should be 5.00. I haven't been sticking with the sig fig rules. Let's actually talk about that. So, I believe I mentioned it before in one of the two previous videos, if not both of them. But when dealing with exponents and logarithms, here's the rule. When you take the log of something, however many sig figs you had before taking the log, that's how many decimal places you get after taking the log. So I had 2 sig figs in 1.0 times 10 to the negative 5. Regardless of how many digits I have before the decimal point, I need to have 2 digits after the decimal point. And going backwards is as you would expect. You just reverse the rules. If I wanted to take the exponential or the anti-log, if I was given a pH of 5.00 and I wanted to figure out what the hydronium concentration was, then I would take the base, which is 10, right? We were doing log base 10, so I would take 10 raised to the negative of whatever the pH is, and that would give me the hydronium concentration. Similarly, 10 to the negative pOH would give you the hydroxide concentration. And however many decimals you have in your pH or pOH, that's how many sig figs you're allowed to have in your final concentration. So in this case, if I did 10 to the negative 5.00, then since I had 2 decimal places in the exponent, I would have to have 2 sig figs in the concentration. I'm not going to calculate it because we already know it's 1.0 times 10 to the negative 5. if I had a pH of 5.0 and I did 10 to the negative 5.0, then since I only had one decimal place in 5.0, I would only have one sig fig in the concentration, and that would just be 1 times 10 to the negative 5 instead of 1.0 times 10 to the negative 5. We'll see more examples of this, and I'll re-emphasize this rule again so that it'll stick. But yeah, if we've got a pH of 5, then what is the pOH? So we can take advantage of the fact that Kw equals the hydronium concentration or hydrogen concentration. I'm not going to keep saying that, but for the first few times I'll say it for emphasis. Hydronium concentration times hydroxide concentration. 1.0 times 10 to the negative 5 times hydroxide concentration is 1.0 times 10 to the negative 14. 1.0 times 10 to the negative 14, assuming, of course, we're at room temperature. If you're not told otherwise, just assume you're at room temperature. What was it? 1.0 times 10 to the negative 5, and then that times hydroxide concentration. Divide by 1.0 times 10 to the negative 5, and you get 10 to the negative 14 over 10 to the negative 5. That's 10 to the negative 9. That's going to be 10 to the negative 9. So 1.0 times 10 to the negative 9 equals the hydroxide concentration. And if you take the negative log of that, then you're going to get a pOH equal to 9. 9.00 to be specific. We had 2 sig figs, so 2 decimal places. Some of you might be noticing a pattern. In our other example, we had a pH of 0 goes with a pOH of 14. Here we've got a pH of 5 goes with a pOH of 9. If you add the pH and the pOH in both cases, the total is 14. Coincidence? Is that a coincidence? Well, of course it's not. It makes sense that the pH and pOH are related because the H, or H3O plus, and OH minus are related. It makes sense that the pH and pOH would be related. In fact, we can prove it rather easily if you know your rules of logarithms. If I take it at room temperature, so 1.0 times 10 to the negative 14 equals the hydronium times hydroxide concentration at equilibrium. Then if I take the negative log on both sides, I end up with negative log of 1.0 times 10 to the negative 14. That's going to be 14.00 equals the negative log of hydronium times hydroxide concentrations. Okay, so the rules of logarithms tell me that the log of a product is the sum of the logs. So of course I'd have to distribute the negative sign over that sum, but essentially we get 14.00 equals negative. Log of a product equals the sum of the logs, so that's log of the hydronium concentration plus the log of the hydroxide concentration distribute the negative, and we end up with 14.00 equals negative log of hydronium plus negative log of hydroxide. Oh, but wait a minute. Negative log of hydronium, that's pH, and negative log of hydroxide, that's POH. 14.00 equals pH plus POH. I must emphasize at room temperature, which is what it will usually be. It'll usually be at 25 degrees Celsius. But every now and then you might get a curveball. You might be given a problem where kW is some other value. So it's very important to remember that this statement is only true for 25 degrees Celsius. Okay, I want to go back to the auto-ionization of water to call to your attention, once again, the fact that water can function as both an acid and a base. There are, in fact, several substances that can function as either an acid or a base depending on the circumstances. Again, that's Bronsted-Lowry acid or base. Anytime I say acid or base from now on, assume it's Bronsted-Lowry unless otherwise stated. But yeah, anything that can function as both, anything that can go both ways, we call that an amphiprotic substance. We call it an amphiprotic substance. Amphiprotic. I don't know much about Latin, but I think everybody knows a few words that start with the word amphi, like amphibian. Amphibians are animals that can live in both the water and on land. What else? I can't think of any other examples off the top of my head. Oh well. Amphiprotic is similar to the word amphibian. Amphi means can use both options, can go both ways, and protic, well, that's related to protons. So essentially, able to accept or donate. Able to accept or donate protons. You probably don't need me to write it out, but sometimes writing it out helps it stick in memory better. Able to accept or donate protons. We've got lots of amphiprotic substances. One example I can think of is the bicarbonate ion, or the hydrogen carbonate ion. HCO3 minus. So it could react with water and remove a hydrogen from it, making H2CO3 plus OH minus. You can also have just lose a proton from here. And let's see, that would give us the carbonate ion and hydronium. So yeah, here the bicarbonate ion functions as a base, and in the green equation it functions as an acid. Very important in light of this, do not assume that the conjugate of bicarbonate is always going to be carbonic acid, nor should you assume that its conjugate is always going to be carbonate. It depends on which way you're going. If I were to ask you what is the conjugate base of carbonic acid, H2CO3, That's going to be easy because carbonic acid can only go one way. Carbonic acid is not amphiprotic. It's always going to act as an acid or just not dissociate at all. So the conjugate of carbonic acid is always going to be the bicarbonate ion. But if I ask you what is the conjugate of the bicarbonate ion, be careful because there's two possibilities. You have to figure out which way you're going first. In this case, the conjugate is the carbonic acid, and in this case, the conjugate is the carbonate ion. Very, very important to remember that. With amphiprotic substances, there's multiple options for what the conjugate could be. And it's not something we haven't seen before. We saw it with water. Sometimes the conjugate of water is hydroxide, and sometimes its conjugate is hydronium. In fact, we see that in both of these equations. So yeah, we've got two examples of amphiprotic substances in both of these equations. Okay. Now I want to talk a little bit about how we can measure the pH of an acid, how we go about doing it in the lab. So the best tool, in my opinion, is some digital tool like what you see in front of you. With these tools, what are they called? pH meters. They can measure the pH to whatever level precision you're willing to pay the money for. It actually mentions under the image that for 3 decimal places, you're gonna need something that's over $1,000. I'm not gonna get one of those. Not worth it. And then they say that this other meter, the red one, it's less precise, but they say it's a far lower price tag. I'm not sure how far lower. But no matter how low it is, I don't really have a need to measure pHs on a daily basis, so it's not something I would use, therefore it's not something I would pay the money for. But you never know, my needs might change. Okay. So, yeah, pH meters can be used. We can also measure acid-base strength using indicators. It's a more qualitative measure, but you've probably heard of, what are they called? pH paper, which typically comes in red or blue strips, and you dip the strip. If you dip it in an acid, it always comes out red. If you dip it in a base, it comes out blue, and that's a qualitative test. It doesn't tell you how acidic something is or how basic it is, but it does tell you at the very least if it's generally an acid or a base. It answers that simple yes or no question. Something that might give you a better idea of pH, while still inferior to the digital tools, is what's known as the universal indicator. This is some type of dye that changes color depending on the pH, and based on the shade of the color, you can sort of guess approximately what the pH is going to be based on the color. But again, if you want precision, you should probably just use the digital tool. And yeah, it's the digital tools, they're less fun, but they get the job done, which is the important thing. So I have something that is probably not the same as this universal indicator, but I've put something together. I put it together this morning, in fact. It's called the red cabbage indicator, and it also gives you a variety of colors, and we're going to demonstrate it, but yeah, there you go. So basic description in case you want to do this at home. It's actually really simple. Get some red cabbage. Preferably get the shredded stuff, because if it's shredded, that's more exposed surface area, and the dye will dissolve into the water much more easily, much faster. Then again, if you have plenty of time, it probably doesn't matter. But yeah, I bought the shredded stuff. I put it in water, let it boil for a while until I saw the color of the water change. Usually you're supposed to get a sort of purple color, a dark purple color, but I got blue. I think temperature affects it, because I remember the last time I did it, which was probably 8 years ago, it did come out purple. Then I put it in the refrigerator and it turned blue. So I think because it's still winter, that's why I got blue stuff. But if you look around online, people say you're supposed to get purple. And yeah, you just filter out the red cabbage shreds. If you like cabbage, I guess you can still eat them. But you filter the shreds out and just get the liquid, and there you have it. That's your indicator. Let's go ahead and work with this stuff. So let me put some paper towels out here, or napkins, I should say, just to make sure I don't accidentally spill anything, just in case. And here we go. So these are kind of a bluish green, not the purple stuff that I was expecting to get, but it is neutral. I haven't messed with it at all. And now I'm going to add some acids and bases to this stuff. So I'll start with my base. For the base, what I'm using is, what do you call it? Just the drain opener solution, which contains a strong base, potassium hydroxide. So I'm going to go ahead and squirt some base into there. And let me stir it a bit. Maybe that'll help the color change go a little faster. Okay, I don't know if it's that visible on screen, but I can tell it's getting a little bit greener. Maybe if I angle it a bit, maybe you can see the color change. Doesn't matter. It'll continue changing as I add more potassium hydroxide and whatever else they put in this drain cleaner. Okay, let's stir that up a bit. Actually, it looks like the way the lighting is working, this location is a little bit better. I'm going to move this out of the way so that I can move this into position. Okay, yeah, now you can see that more clearly. It's past the green phase now, it's kind of a golden yellow. And I think if I keep going, the color is eventually just going to fade completely. Yeah, that's kind of a golden yellow. Maybe it skipped over orange, or maybe it doesn't go orange at all. I'm usually not too careful when I do this experiment. Okay, let's stir that up some more. Okay, yeah, that's turning into a brighter yellow, or I guess you could argue it's orange. Alright, and I think that's a good enough place to stop. Now let's try adding an acid. Whoops, wrong container. There we go. So for my acid, I'm just going to use plain old vinegar. For my base, I was planning to use baking soda, but Baking soda is so weak that I had to dump in a lot in order to see a color change. So for those of you at home, I would prefer if you used baking soda for your base, just because, it's safer to deal with. You don't want to get drain cleaner on your hands. It's kind of watered down, so the effects won't be immediate, but it is more dangerous stuff, so I would prefer that you use baking soda. Anyway, adding in, this is apple cider vinegar, but vinegar nonetheless. And you can see the effect almost immediately. There's this sort of purplish pink color starting to spread. Okay, yeah. So this is the purple color that I was supposed to get after boiling my red cabbage, but for whatever reason, and I think it's because of the temperature, because it's cold in my kitchen, I got the blue stuff instead. If I did have this purple stuff from the beginning, it would be easy to turn it blue with baking soda, but it was already blue, so baking soda wasn't going to cut it. Whoops. Uh-oh. No. I accidentally put the dropper in the potassium hydroxide. Okay, new dropper. Let's add some more vinegar there and stir. Some more. I think it goes all the way to a light pink. Instead of vinegar, you can also use the juices of citrus fruits, oranges, lemons, limes, grapefruit. And yeah, if you use lemon juice, well, congratulations. Now you know how they make pink lemonade. I don't know if the red cabbage indicator is what they actually use to make the pink lemonade pink, or if they just use ordinary food coloring, but now I've ruined pink lemonade for you, so enjoy ruining it for other people. Spread the misery, share the pain. I can't really tell if the color is changing anymore, but I'll try adding a few more doses. Okay, maybe 2 more. And try stirring. Okay, 1 more. 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 Just 1 more. Okay, 1 more. Some of you probably got the reference I was going for there. Others are probably confused. I guess that is kind of red. Yeah, it feels kind of red. Okay, well, experiment over. So I don't want to accidentally knock this stuff over, especially not the potassium hydroxide, so give me a minute to put these away. I'll be right back. Alright, I'm back. Had a little bit of an accident. Accidentally got some of the drain cleaner on my hands and had to make sure I thoroughly washed it off. And did I spill any on the paper? It doesn't look wet anywhere, so yeah. Okay, dunking this in the trash. Okay, where do we want to go from here? Well, I guess this isn't really something you need to know, but I guess I can describe why the color change is happening. So, the dye that you can extract from red cabbage and other natural sources, it's a substance that's basically an acid or a base. In fact, it's amphiprotic because, as you saw, it can it can react with acids or bases. It can function as a proton acceptor or a proton donor. I couldn't find the exact compound that is extracted from red cabbage, but I did find a diagram that shows you what happens with a similar compound. So, this is a compound known as an anthocyanidin, which, at different pH levels, it gives you different colors because at different pH levels, the structure of the compound changes and the way that light passes through it also changes. So, you see at the very far left, that's under the most acidic conditions. That's where you basically have as many protons donated to the molecule as possible. If you look just to the right of it, you'll see that, wait a minute. Do I have that right? Yeah. So if you add some hydroxide to it, then you'll see there's an additional OH on the top right ring of the compound when you compare the one in the red zone versus the one in the pink zone. And if you go to the next one to the right, you see that one of the OHs lost its hydrogen, which is what happens as you add more and more base. You decrease the amount of hydrogen or increase the amount of hydroxide. So yeah, some hydrogen is being removed there. And then if you go to the next phase, it looks like another OH has been added to the ring on the top right. And if you continue to the right, the next one, which is second to last, looks like you've got an oxygen sticking out there at the top that's lost its hydrogen, donated it. And for the very last one, you've got two oxygens sticking out near the top that have lost their hydrogens. So, yeah, you can change the structure of certain molecules, which affects the way light passes through them. And if you want to see the original source of this image, it came from, I think, a biology paper. I didn't read the whole thing. I just really cared about the image. But if you want to see the source, there's your citation. The link is at the very end of that whole thing. It's probably advanced stuff that most of you guys wouldn't be able to handle anyway, but then again, I don't know much about biology, so maybe you are capable of understanding it. If you know more biology than me, you probably stand a better chance. Okay, so yeah, pH indicators, acid-base indicators, are themselves acids and bases. And of course, the problem with these more universal indicators is that they've got a variety of colors which I guess you can use to imprecisely pinpoint pH, but it's usually easier to work with these, I guess I'll call them binary pH indicators, that only have two colors. below a certain pH, it's one color, and once you get past that pH, it's another color. The one you've probably worked with the most in school is the third one from the bottom, phenolphthalein, which is clear under a pH of approximately 9 and turns into a pink color past a pH of 9. Now, some of you might be going, wait a minute, in class we were using it to determine whether or not we got to a neutral state. So, you're telling me this whole time we were finishing our titrations at a pH of 9, not 7? How does that work? How is that even legal? I'll explain that in the next video. There's actually a very good mathematical reason for why it isn't a problem. But yeah, when you finish your titration, you finish it at the end point, not the equivalence point. And the end point is usually not that far off from the equivalence point, so it won't hurt your calculations all that much. If you need to be more precise, you can always use those digital pH meters, but for academic purposes, for high school and early college purposes, phenolphthalein is perfectly fine. Okay, I think it's time to look at some problems. Or is there something that I need to cover first? I feel like there's something I need to cover first. Oh well, if there is something that I'm forgetting, it'll come back to me as we look at these problems. Okay, first problem, or first two. Write equations that show NH3 as both a conjugate acid and a conjugate base. Okay, that shouldn't be too much of a challenge. Okay, NH3 is a conjugate acid and NH3 is a conjugate base. So no matter what reaction I have, NH3 needs to show up on the product side. And I'm not going to write the phases just to save time. Okay. So if NH3 functions as a conjugate acid, that means going in the reverse it would have to lose a hydrogen, so that's the amide ion, NH2-. Okay, and I guess I'll just react it with water then, NH2- plus H2O. The other reactant doesn't always have to be water, by the way. It's just going to be the most common one. NH2- plus H2O is going to give us NH3 plus OH-. Okay, there we go. And for this one, if it's a conjugate base, that means the acid must have been NH4 plus. And I guess just to add some variety, let's do something other than water. Let's do the fluoride ion. And so we get NH3 plus HF. Okay, there we go. That wasn't too bad. Then they say write equations that show the dihydrogen phosphate ion acting both as an acid and as a base. Okay, so basically the same as number one, but you want H2PO4- to be on the reactant side in both cases. You can do that on your own. Let's move on to another one. Show by suitable net ionic equations that each of the following species can act as a Bronsted-Lowry acid. I mean, all you'd have to do is put them on the reactant side and show them losing a hydrogen. And they say net ionic equations. So cancel out any spectator ions that show up on both sides. Well, I don't think we're going to have I mean, in the case of HCl, maybe. Yeah, I don't get why they're saying use suitable net ionic equations. I think just the normal molecular equations are going to be the net ionic equations for all of these. But there will be a point where we do get some spectator ions, so that is coming. Just not yet. I don't think we need to show this, but I'll just do one of them. Let's do 3D. Let's do problem 3, part D. Okay, so that is acetic acid. That is acetic acid. CH3CO2H, that's CH3 CO2 H. Okay, plus water gives you the acetate ion, CH3COO minus. You don't have to write it out as a Lewis structure. I'm just doing that for, I guess, illustrative purposes. Plus hydronium. All right, and there's problem 3, part D. It is the net ionic equation. No spectator ions here. Also, if we look at something like what we've got up here, fluoride is not a spectator ion because HF is not completely soluble. It's not a strong electrolyte. We'll talk about electrolytes again later on in this video, so if you've forgotten what electrolytes are, we'll review them, but you really shouldn't have forgotten because we've mentioned them recently, I think in video number 11. Okay, do we need anything from number 4? No, it's basically the same, and I'm guessing the next page is gonna be similar but show that it's a base, right? Yeah, show by suitable net ionic equations that each of the following species can act as a Bronsted-Lowry base. See, if they showed the counter ions, then you know what? I'm going to do that. Let's do 5D, and I'll show you why they're emphasizing net ionic equations. So for 5D, instead of the cyanide ion, I'm going to say sodium cyanide. If I put sodium cyanide in water, the cyanide ion is going to accept a proton from water, so we'd get the sodium ion by itself plus HCN plus OH minus. Now, if you write the total ionic equation, sodium cyanide, anything with a group 1 metal is soluble. It dissociates completely. So NaCN is really Na plus Cn minus. It's already dissociated before the reaction even begins, assuming you stirred well. or it was already in solution. Okay, so sodium ion is the spectator ion. We also call it the counter ion because it's there to counter the charge and make sure that your solution is still neutral overall. So they're there, but they're not the most important feature of the reaction. Okay, and there you go. So your net ionic equation is cyanide ion plus water gives you cyanic acid plus hydroxide. Okay, and let me put it up on screen again in case you want to do the other examples yourself. I'm just going to move on. Number 7, what is the conjugate acid of each of the following, and what is the conjugate base of each? Okay, so these are all amphiprotic, and yeah, we want to find both of their possible conjugates. Okay, OH minus, if it gains a proton, it becomes water, which would be its conjugate acid, and if it loses a proton, then it becomes the oxide ion, which is its conjugate base. Water, we've already seen. The bicarbonate ion, we've already seen. Let's see. Ammonia, we've already seen, right? The amide ion and the ammonium ion. Bisulfate, pretty much just like bicarbonate. Yeah, you can do these on your own. I don't think they're that tough. We've already seen examples of that. Let's see what else we've got. Number 9, identify and label the Bronsted-Lowry acid, its conjugate base, the Bronsted-Lowry base, and its conjugate acid in each of the following equations. I don't think we really need to do this, but I'll just do one of them for the sake of example. And I see they're not using equilibrium arrows, but that's okay. Maybe it's just harder to type them in, and they wanted to save time. Let's do, oh, I haven't told you which one I picked. Let's do C. Let's do C, H2SO4 plus Cl minus. Okay, so who's losing a proton? H2SO4, sulfuric acid. So there's your acid. That means this has to be the base. That makes this the conjugate base. And this becomes the conjugate acid. And there we go, done. That wasn't hard. In case you were unclear on what to do, now you know. It's really that easy. Is number 10 the same? Yes, number 10 is the same. Okay. Next set. What are amphiprotic species? Illustrate with suitable equations. We already did. And our example was the bicarbonate ion. Number 12, state which of the following species are amphiprotic and write chemical equations illustrating the amphiprotic character of these species. Simple enough. We know water is amphiprotic. The dihydrogen phosphate ion is amphiprotic. It's just like the bicarbonate ion. It can gain a hydrogen to form phosphoric acid, or it can lose a hydrogen to form the hydrogen phosphate ion, one hydrogen. S2 minus, it can't lose any protons because it doesn't have any, so it cannot function as an acid, which means it's not amphiprotic. It can only function as a base. Carbonate, same deal. It can only function as a base because it doesn't have any protons it can donate. HSO4 minus, the hydrogen sulfate or bisulfate ion, can go both ways. Can gain a hydrogen and become sulfuric acid, or can lose a hydrogen and become sulfate. So that is amphiprotic. 13, basically the same as 12, so we'll skip. 14, is the self-ionization of water endothermic or exothermic? The ionization constant for water is 2.9 times 10 to the negative 14 at 40 degrees Celsius and 9.3 times 10 to the negative 14 at 60 degrees Celsius. Okay, so at the higher temperature, you've got a higher dissociation constant. Equilibrium constant goes up with increasing temperature if the reaction is endothermic. Remember the previous video? We talked about this when covering Le Chatelier's principle. Higher temperatures drive the reaction further to the right, which increases the equilibrium constant if the reaction is endothermic. So, self-ionization of water, endothermic. Okay, let's look at the next set. Explain why a sample of pure water at 40 degrees Celsius is neutral, even though the hydronium concentration is 1.7 times 10 to the negative 7. Kw is 2.9 times 10 to the negative 14 at 40 degrees Celsius. Okay, so this is what I was warning about. pH equals 7 does not always mean neutral. It means neutral at 25 degrees Celsius. At a higher temperature, neutral might be at a different pH level. So let's go ahead and do the math. I mean, I trust their calculation, but they do want us to, prove it. So let's go ahead and do that. We've got 2.9 times 10 to the negative 14 is going to equal the concentration of hydronium times the concentration of hydroxide. Now, in a neutral substance, the amount of hydronium and hydroxide should be the same at the end in just neutral water, I should say, or a neutral solution. It doesn't have to be water. Salt water, for example, is neither acidic nor basic because sodium chloride doesn't really have acidic or basic properties. We'll talk about the acidic and basic properties of certain salts later. Anyway, so both of them should have the same final concentration. So if this has a concentration of x, then so does this one, equals x squared. Take the square root on both sides. Square root of 2.9 times 10 to the negative 14. Let me switch to scientific mode. Is 1.7 times 10 to the negative 7. 1.7 times 10 to the negative 7, and yeah, there we go. The pH associated with that, they didn't really ask for it, but the pH is going to be, let's see, negative log of 1.7 times 10 to the negative 7. That equals how many decimal places? I've got 2 sig figs before taking the log, so it should be 2 decimal places. So pH equals 6.77. Okay, so that's the pH of a neutral solution at 40 degrees Celsius. Okay, next up we've got, is 16 the same? Oh, well, we already kind of did that. So it says calculate the hydronium and hydroxide concentrations of pure water. It's 1.7 times 10 to the negative 7. The pH and pOH, they're going to be the same. Oh, actually, no. The pOH is going to be different. The pH is 6.77. The pOH is going to be 14. Oh, no. No, the pOH is also going to be 6.77. Yeah, the pH and the pOH are going to be the same. They don't add up to 14 because it's not at 25 degrees Celsius. They add up to whatever 2 times 6.77 is. Okay. 17, the ionization constant for water is 9.311 times 10 to the negative 14 at 60 Celsius. Calculate the concentrations, pH and pOH for pure water. You know how to do that, so I'll skip 18. Calculate the pH and pOH of each of the following solutions at 25 degrees Celsius for which the substance is ionized completely. Okay, assuming complete ionization. Simple enough. So you do the stoichiometry, figure out the hydrogen, hydronium, or hydroxide concentrations, and calculate. Let's put together this flowchart that I forgot to write down earlier. So it's pretty easy once you understand this flowchart. It's pretty easy to quickly decide where to go when trying to figure out pH, pOH, and hydrogen and hydronium concentrations. So H plus or H3O plus is what we'll have in this corner. And in this corner, we'll have the concentration of OH minus. Let's see. Do that. And then, of course, down here we'll have pOH. Over here we'll have pH. We're going to have a connection between those and a connection between these. So, going from concentration to pH, you take the negative log of H plus or negative log of H3O plus. And going in the opposite direction, you do 10 to the negative pH. Okay, similar stuff here. So going from pOH to hydroxide concentration, you take 10 to the negative pOH. And I guess I should show where this comes from for those who don't know the math. So let's just do it with pOH. If pOH equals negative log base 10 of hydroxide, I guess that's not really readable, then multiply by negative on both sides, you get negative pOH equals log base 10 of hydroxide. To cancel log base 10, you would want to exponentiate with base 10. So 10 to the negative pOH equals 10 to the log base 10 of hydroxide. And of course 10 and log base 10 are inverse functions, so they cancel out, leaving you with 10 to the negative pOH equals the hydroxide concentration. Some of you probably didn't need that proof, but for the ones who did, there you go. Something similar comes out of trying to do this for pH. Anyway, back to where I was. So going from hydroxide concentration to POH, you just take the negative log of hydroxide. And then going back and forth between these, you would use Kw equals, I'll just use hydronium times hydroxide. And POH and PO and pH, you can say pKw, the negative log of Kw, equals pH plus POH. And then at 25 degrees Celsius, you can say 14 equals pH plus POH, which is what it's usually going to be. All right, so yeah, remember that flowchart if you're having trouble keeping it all organized in your head. Anyway, back to the problem. So, which parts of 18 do I want to do? Let's do B and D. Let's do B and, or, okay, B and C. Let's do B and C. So we've got 0.0143 molar sodium hydroxide. And they said assume this dissociates completely, giving us the sodium ion and the hydroxide ion. Single arrow, not double arrows. Of course, this decreases by 0.0143, and these increase by 0.0143 each. So yeah, your final concentration of hydroxide is 0.0143. And if we take the negative log of that, what do we get? 3 sig figs, so I'm going to need 3 decimal places. Negative log of 0.0143 is going to be 1.845. 3 sig figs, 3 decimal places. 1.845. Okay. To get the hydronium concentration, I can either just use Kw, assuming this is at room temperature, just use Kw divided by this concentration, or I can calculate the pH. This is our POH after all. I can use this to calculate the pH and then use the pH to calculate the hydronium concentration. So I've got 2 different routes. I'll go ahead and calculate the pH. Assuming this is at room temperature, did they? Yeah, they did say it was at room temperature. So assuming this is at, not assuming, it is at room temperature. Since it's at room temperature, pH is going to be 14 minus 1.845. So 14 minus 1.845. I know the 14 isn't really exact, but I'm going to treat it as having 3 decimal places anyway. So yeah, I'm brushing off some of my sig fig rules here. Actually, let me check. So it's Kw is, if I add 1 more sig fig to it, it would be 1.01 times 10 to the negative 14. So if I take the negative log of that, that's going to be 13.995. Yeah. Okay, so I'm going to cheat a little bit and treat it as being 14.000, but if you have it to 3 decimal places, it's actually 13.995. So 1.845 subtracted from 14 is going to be 12.155. Okay, if we calculate the hydronium concentration from there, hydronium concentration is 10 to the negative 12.155. 3 decimal places in the exponent, 3 sig figs in the resulting number. So 10 to the negative 12.155 is going to be 3 sig figs. That's going to be 7.00 times 10 to the negative 13. 7.00 times 10 to the negative 13 molar. pH and pOH, by the way, I forgot to mention, are unitless. We don't have any units for pH and pOH. Okay, so that was the sodium hydroxide example. Did I say part C? Let's actually do part D. Let's do part D after all. It has something that I want to emphasize. So for part D, we've got calcium hydroxide 0.0031 molar. 0.0031 molar calcium hydroxide. Remember that when calcium hydroxide dissociates, you get 2 equivalents of hydroxide. We get calcium ion plus 2 hydroxides. So we get 0.0031 molar of the calcium ion, which is useless to us, and we get 2 times that, so 0.0062 molar of the hydroxide ion. Everything else is pretty much the same as before. So let me just do some quick calculations here. pOH is going to be negative log of this, so negative log of 0.0062, and that had 2 sig figs, so my pOH needs to have 2 decimal places. That's going to be 2.21. And then pH is 14.00 minus that, which is 11.79. And the hydronium concentration is going to be 10 to the negative 11.7, or 10 to the negative 11.79, I should say. And let's see, 2 decimal places, 2 sig figs, so that's going to be 1.6 times 10 to the negative 12. So yeah, nothing too hard to do, but I guess my goal with this is to help the new sig fig rule for exponents and logarithms sink in a bit. What else do we have? 19, calculate the pH and the pOH of each. Okay, so basically the same. 20. What are the pH and pOH of a solution of 2 molar HCl, which ionizes completely? Same thing. 21. What are the hydronium and hydroxide ion concentrations in a solution whose pH is 6.52? We've already done that. If you know the pH, then you can get the pOH by subtracting from 14. I'm assuming this is at room temperature. If they don't tell you otherwise, that's a reasonable assumption. And yeah, once you've got the pH and the pOH, 10 to the negative 6.52 is your hydronium concentration, and 10 to the negative whatever the pOH is gives you your hydroxide concentration. We've already shown how to do that. 22. Calculate the hydrogen ion concentration and the hydroxide ion concentration in wine from its pH. See the figure for useful information. I actually forgot to show this one, but I do actually have that visual. So let's pull it up. There it is. Yeah, so of course, pH is a way of measuring the relative strengths of acids and bases, and just to give you a sense of what different pH values represent, they give you some simple examples. So let's see, you've got wine appears to be somewhere between 3 and 4 pH, or 11 and 10 in terms of pOH. Okay, and that puts it at a hydronium concentration between 10 to the negative 3 and 10 to the negative 4. I guess they want you to assume its pH is exactly halfway between 3 and 4, which would be 3.5. But aside from that, you know how to do the rest. If you have pH, 10 to the negative pH gives you hydronium concentration. Been there, done that. Okay. I think one more sheet before we talk about some new topics. 23, same as the previous one. Use the chart that I just had up to calculate some concentrations, in this case for lime juice. 24, the hydronium ion concentration in a sample of rainwater is found to be 1.7 times 10 to the negative 6 molar at 25 Celsius. What is the concentration of hydroxide? So the most direct way would just be use Kw divided by that concentration to get the hydroxide. And 25 looks like it's basically the same thing, but reversed, where they give you the hydroxide and ask for the hydronium. Okay, nothing too hard there. That isn't really the meat of this chapter anyway. It's just kind of introductory warm-up material. So now it's time to get into the nitty-gritty and apply some more equilibrium concepts to this. So I must emphasize that acids and bases are electrolytes. Acids and bases are electrolytes. Not all electrolytes are acids and bases, but all acids and bases are electrolytes. And you may remember that depending on whether they dissociate completely or only dissociate partially, you can categorize electrolytes into the strong and weak categories. So we've got strong acids and bases are strong electrolytes. They dissociate completely. And weak acids and bases are weak electrolytes. weak acids and bases are weak electrolytes. How do you know if a particular acid or base falls into the strong electrolyte category? Memorization. Memorization. All acids and bases are weak electrolytes except for I'll list the strong acids and bases. Your strong acids are hydrochloric, hydrobromic, and hydroiotic, or hydriotic if that's how you prefer to pronounce it, sulfuric, nitric, perchloric, and depending on who you ask, chloric acid. So for this one, I would add a note and say it's debatable. Maybe debatable isn't the right term, but depending on who your instructor is, some instructors will insist that you include it in the list of strong acids, and some will insist that it's actually a weak acid. And the reason is because actually all of these strong acids, they don't actually dissociate completely. It's more like they reach an equilibrium that is so heavily biased towards products that you might as well treat it as if it's not an equilibrium reaction at all. You might as well treat it like it goes all the way to the right and no reactant remains. But yeah, we're going to treat them like they go all the way to the right. They always form products leaving no reactants behind. It'll simplify our calculations, and even if you did want to look up the equilibrium constants for each of these, it's going to be a high enough value where if you do try to use equilibrium calculations to figure out how much you end up with in the end, after rounding to the appropriate number of sig figs, you will realize that you could have just taken the easy route and assumed that it goes to completion. So you really will be wasting your time doing that. Maybe if you're working for NASA, you'll have to be more precise, but for our purposes, no need. You can assume all of these will dissociate to completion, except for sulfuric acid. So sulfuric acid is a special case. Sulfuric acid, only the first proton, only the first hydrogen. The second hydrogen is harder to lose. So for sulfuric acid specifically, you can say H2SO4 with water just goes straight to HSO4 minus plus hydronium. That's fine. But the the next hydrogen from the bisulfate ion, this one doesn't necessarily, you don't lose all of your bisulfate to form more hydronium. So that one is an equilibrium process. So step 1, non-equilibrium. Step 2, equilibrium. Be very careful about that. Some teachers will probably ignore that either because they want to make it easier for you or because they don't know, or both. Given the state of our education system, it's anybody's guess. But yeah, the truth is that only the first hydrogen in sulfuric acid is strongly acidic. Okay, so those are your strong acids. As for your strong bases, you can remember them based on their positions on the periodic table. So, it's really simple. All of the group 1 metals and some of the group 2 metals. Lithium hydroxide, sodium, potassium, rubidium, cesium, all of their hydroxides are strong bases. For group 2, skip beryllium, skip magnesium, calcium hydroxide, strontium hydroxide, and barium hydroxide. Radium, I guess, would count, but I believe it's radioactive and unstable, so we can't really make compounds with it, if my understanding is correct. But yeah, lithium through cesium, and I guess francium if you could make compounds with it, and calcium through barium. It's that simple. The hydroxides of those metals, those are your strong bases. All other hydroxides are going to be weak. So what color should I use? I guess I'll go with orange. So lithium, sodium, potassium, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. And let's see, skip beryllium and magnesium, we would have calcium hydroxide, rubidium, or no, not rubidium. What's next to rubidium? Strontium. Strontium hydroxide and barium hydroxide. So most of the strong acids and bases are what we would call monoprotic. Most of them are what we would call monoprotic. So let's talk about the concept of protonicity. It's not really that hard of a concept to understand. Protonicity. So monoprotic means you either donate 1 proton or you accept 1 proton. So HCl, HBr, HI, HNO3, HClO4, and HClO3, they all have 1 proton to lose. And these group 1 hydroxides, lithium, sodium, potassium, rubidium, and cesium hydroxides, they each have 1 hydroxide that will act as a proton acceptor. So they're all monoprotic. Diprotic means you either have 2 hydrogens or 2 hydroxides, or you're capable of receiving 2 hydrogens. Earlier we saw that the oxide ion can act as a base. It can take 2 hydrogens. If it takes 1, then it gives you hydroxide, and if it takes another one, then you get water. So I guess you could count the oxide ion as being diprotic, or maybe even triprotic if you go all the way to hydronium. Maybe the oxide ion isn't the best example. It feels like a weird case, and I feel like I might be saying something wrong here. Okay, scrap that. Maybe that's not the best example. Diprotic, you've got your sulfuric acid, your calcium hydroxide, strontium hydroxide, and barium hydroxide are all diprotic. They can either gain or lose 2 protons, and I guess for anything above that we just say polyprotic to be more general. 3 would be triprotic. 4, if that even exists, I've never seen an example of it. Wait a minute. Yes, I have. We had it on the screen earlier. The color changing pigment thing. It changes in 4 different steps, either receiving or donating 4, or was it 5? How many steps was it? Let me put it back up on screen. Let's see, 1, 2, 3, 4, 5. Yeah, there's 6 compounds there. So going from the far left all the way to the far right, or vice versa, you're either losing or gaining 5 protons in successive steps. Okay. Got that cleared up. So yeah, monoprotic, diprotic, polyprotic, and I guess you can add the appropriate prefix if you want to be specific. If it's 3, it's triprotic. If it's 4, it's tetraprotic, and so on. The usual prefixes apply. But you're probably not going to see anything beyond monoprotic or diprotic most of the time. Okay, so there's protonicity and there's your strong acids and bases. So anything else is considered weak. But what exactly is meant by strong? Let's not forget. When I say strong acids and bases, I mean that they're strong electrolytes. I don't necessarily mean that their pH or pOH is exceptionally high or exceptionally low. I just spilled some potassium hydroxide on my hand earlier during this recording when I was trying to put away the materials from our little experiment. But as you can see, my hands didn't melt off. Can you see my... Yeah, okay. Now they're fully on screen. But yeah, my hands didn't melt off, so what's the deal? Well, concentration along with acid-base strength ultimately determines pH, and pH determines how damaging to your skin an acid or base really is. So the potassium hydroxide I spilled on my hands was fortunately at a low enough concentration that I had enough time to wash it off my hands before it started taking effect on my skin. Sometimes you will hear, and I have to warn about this, sometimes you will hear or you'll see problems that will say something like hydrofluoric acid is a strong acid used in whatever process. They don't mean that it's strong in the sense that it's a strong electrolyte. They mean it's strong in the sense that it's stronger than most other acids. So sometimes they'll do that, and I do think it's a stupid thing to do. I hate when I see it in textbooks, but be warned, sometimes that'll happen, so you just need to infer from context what they mean by strong, because sometimes they'll use strong to describe something that actually falls into the weak category. So yeah, anything in the strong category, single arrows. Anything in the weak category, equilibrium arrows. Always, always, always. And weak acids and bases are going to be our primary focus for these next 2 videos, actually. So for weak acids and bases, we have equilibrium constants, which I kind of talked about a little last time. I think it was towards the end of the previous video. We have Ka and Kb values. The acid dissociation constant and the base dissociation constant. And I guess some books also call them ionization constants. as opposed to dissociation. There are people who nitpick about the difference between dissociation and ionization. I don't. I use the terms interchangeably, and maybe that's irresponsible of me, but I don't really see much reason to care about the difference because the difference is so subtle. I guess I'll talk about it a little bit. So, dissociation is something like when, say what you have up here. When you have basically an ionic compound that separates into its ions, they call that dissociation. On the other hand, if you have something like let me see. On the other hand, if you have something like, well, maybe the reverse of this. If you have something like NH3, which is not ionic, it's molecular, reacting with water, it turns into something ionic. Therefore, they call that ionization, the process of becoming ionic. But really, to me, the difference isn't anything worth fighting over, so I'm going to use the terms interchangeably. And some people will be mad about that, and so be it. Anyway, acid and base dissociation constants. So these are the equilibrium constants for the dissociation process for an acid or a base, a weak acid or base in water. So Ka, I guess I'll write the equations, the chemical equations first before I write the formulas. So Ka, if I have some generic acid, let's call it HA, and I react it with water, then of course it'll form the hydronium ion, and you'll be left with some conjugate A-. On the other hand, for a base, let's say my base is B, and I react it with water, then it will take a hydrogen off of water, becoming BH+, and leaving behind a hydroxide. Okay, so of course the water is going to be liquid, so it's not going to contribute to the equilibrium constant. Everything else is going to be aqueous. And so if we write the equilibrium constants for these, they're always going to be the same format. So an acid dissociation constant is the hydrogen or hydronium concentration times the conjugate base concentration divided by the original acid concentration. And Kb, similar story, it's going to be the conjugate acid concentration times the hydroxide concentration. I guess I'll write the hydroxide first, just for the sake of pattern matching, over the original base. I used B for the base here. Some textbooks will just use A- as the base, and that's fine. I think I'll actually do that at some point, maybe in a few minutes actually. But yeah, there you go. So assuming these are final concentrations, those ratios would be equal to the acid or base dissociation constants of various weak acids and bases. So how do you get these values? Well, either through experiment, you measure the concentrations and you calculate it, or through our good old handy-dandy data tables. Is this going to tip over? No. So yeah, there's a bunch of equilibrium constants for a bunch of weak acids. I don't know if you can see that very clearly, but it's okay. I'm gonna read them and write them on the page as needed whenever we run into whichever weak acids or bases we have. Speaking of my weak bases, there's the table for my weak bases. Not a whole lot. And that appears at first to present a little problem for us, but there is a solution for it. So, let me return this back to its normal position. Is that right? Doesn't. Oh, no, it's just the papers that are shifted. Okay. Yeah, looks like we are back to our original angle. I can never tell with this thing. I know you can't see this, but I don't even know how to describe them. There are these grooves in the camera and the stand that are supposed to line up when it's at that perfect 90-degree angle, but every time I try to line them up, it still comes across as being a little tilted when I look at the screen. So I don't know. Maybe it's the angle that I'm using to look at the grooves when I try to line them up. But anyway, let's go ahead and talk some more about Ka and Kb. So I have, for example, the Kb value for ammonia. I have Kb for NH3, which is equal to, and these are all taken at room temperature, which is equal to 1.8 times 10 to the negative 5. So that's Kb for ammonia. Now, if I have a reaction involving ammonia as the base, so NH3 plus water, giving us ammonium ion plus hydroxide ion, then I can do some equilibrium calculations with this like I did in the previous video. So if I were asked, for example, if I were asked what's the pH of a, let's say, 1.5 molar solution of ammonia, then I could do that. I could set up my ice table and all that. So let's see, we've got 1.5. Doesn't matter how much water, it's not going to contribute to the equilibrium constant. I've got, well, you start with 0 here and start with 0 here. And this is going to decrease by x. This is going to increase by x. This is going to increase by x. And so the final concentrations are 1.5 minus x and x and x. And so you can say Kb is going to be equal to 1.8 times 10 to the negative 5 is going to be equal to x times x over 1.5 minus x. X squared over 1.5 minus x. Now, you can multiply the 1.5 minus x over to the left-hand side, and then I guess move everything from the left-hand side over to the right-hand side by addition or subtraction, and solve yourself a quadratic equation. Or maybe we don't have to solve a quadratic equation. Maybe 1.5 minus x is still approximately 1.5. Maybe 1.5 minus x is like 1.499 or something, and it rounds back to 1.5 anyway. So there is something that a lot of teachers ask you to use, which is the 5% rule. I don't really like it because you know what I always say, there are no rules in chemistry. But the 5% rule, or the 5% test, basically goes something like this. If the dissociation constant, whether it's acid dissociation or base dissociation, I'll just use base for my example. If Kb over concentration of your base times 100% is less than 5%, then X is negligible and when we say negligible, we mean negligible in comparison to the starting concentration. X is negligible to C. Usually the starting concentration is something that we call little c. So in this example, little c is the 1.5 molar original concentration of the ammonia. I don't really like this test because it's not going to always work. It's usually going to work. And, you know, a better rule of thumb is just go ahead and assume the X is negligible anyway. And if it's not, then once you perform your calculation, you're going to get a value that doesn't make sense. So that's what I'm going to do. I'm going to assume 1.5 minus X approximately equals 1.5. So I guess I'll write it here. Assume 1.5 minus X approximately equals 1.5. Then my equation becomes 1.8 times 10 to the negative 5 equals x squared over 1.5, which is much easier to solve because you multiply by 1.5 and take the square root. No quadratic equation needed. Let's try that and see what we get. 1.8 times 10 to the negative 5 times 1.5 is 2.7 times 10 to the negative 5, the square root of which is 5.2 times 10 to the negative 3. Okay, so under my assumption, I'm getting x equals 5.2 times 10 to the negative 3. Now, is that really negligible? Well, let's try. Is 1.5 minus 5.2 times 10 to the negative 3 still approximately 1.5? 1.5 minus 5.2 times 10 to the negative 3 is equal to, I'm going to list all the decimals here, so I'm getting 1.5 minus 5.2 times 10 to the negative 3 is equal to 1.4948, which when you round it to 1 sig fig is still 1.5 anyway. So yeah, in this case we got away with our assumption. Now if you do still want to use the 5% test, then I guess I should show how that works. Just an example. So you would do 1.8 times 10 to the negative 5 divided by 1.5, the starting concentration of, in this case, our base. And then that's 1.2 times 10 to the negative 5, which is way less than 5%. So you can reasonably expect that the x is indeed negligible. I mean, some people say 5%. I feel like 1% would be safer, but Apparently under 5% works. I don't know who came up with that figure or if it was just arbitrary, but all I do know is that I don't like it. Okay, so that's great. Now let's do another problem with an acid dissociation. Now let's do one with an acid dissociation. So let's do... Let's do ammonium. Let's say I've got 0.053 molar of ammonium, and I put it in some water. And I form NH3 plus OH minus. Oh, I never finished answering the original problem, did I? Hold on, I'm getting ahead of myself. The original question was, what is the pH of a 1.5 molar ammonia solution? Well, now that we know X was equal to the final concentration of hydroxide. So take the negative log of X, which was 5.2 times 10 to the negative 3. That's your POH. So negative log of 5.2 times 10 to the negative 3. That's 2 sig figs, so I get 2 decimal places. 2.28 is my POH. I guess I'll try to squeeze that in here. POH equals 2.28. which means my pH, assuming this is room temperature, is 14 minus that. 14.00 minus 2.28 is 11.72. 11.72. And then, yeah, there you go. That's our pH. So it's above 7, which means it's highly basic. Not a surprise, considering you added a base to water. You would expect it to be basic and not acidic. Okay, now then, back to this new problem that I started. Wait, oh, it's not OH minus, it's hydronium. Okay, there we go. So same question, what is the pH of a 0.053 molar ammonium solution? So of course this ammonium wouldn't just be tossed in alone in the water, it would be tossed in with some sort of counter ion, which we've already canceled out. For example, maybe it's the chloride ion. Maybe we put it in the form of ammonium chloride, but it's a spectator ion. It's not going to affect anything. Just know that the counter ions, while we don't need to have them in our equation, they are still there. They do serve a purpose, which is to balance out the charge. No charged solutions. That'll be important when we get to electrochemistry, which I think is going to be video number 17. But yeah, let's carry on with this problem. So these both start at 0, of course. So this is going to decrease by x. These are each going to increase by x, since you've got 1 to 1 to 1 mole ratios. If this is foreign to you, review the previous video, because in this video and the next video I'm going to assume you're on top of your ice tables and even at the point where you don't need to actually draw out the table. Okay, so yeah, final concentrations are 0.053 minus x and x and x. So your Ka of, lowercase a. I guess it doesn't really matter, but I always see it as lowercase a and b for acid and base dissociation constants. Anyway, Ka of ammonium equals products over reactants. Water doesn't count because it's liquid. That's x times x, which is x squared, over 0.053 minus x. And of course, let me rewrite it. Equals x squared over 0.053 minus x. Okay, and hopefully this x is going to be negligible. It often is because these k values are small enough that it's possible, but in some rare instances you will still need to do the quadratic formula, so, can't win them all. Anyway, we've got a different problem at our hands. We don't know the Ka value for ammonium, and in fact it's not listed in my data table. It's not listed in any data table in any chemistry textbook I've ever seen. So if you're looking in the back of your chemistry textbook to find the acid dissociation constant of ammonium, you're not going to find it. Why? Well, turns out that it's related to the base dissociation constant of ammonia, so you don't need to list a separate value for ammonium. Turns out that they're related. So I'm going to state the relationship here and use it, and I'm going to prove it after we finish this problem. So it turns out that for a conjugate pair, only if they're a conjugate pair, for a conjugate pair, Ka times Kb is equal to Kw. This is only true for a conjugate pair. Also, be careful about what your conjugate pair is when dealing with amphiprotic substances. We might see an example of that at some point. If not, I guess I'll try to remember and pull one out if they don't have one in the problems that I've prepared anyway. I'm hoping I don't forget. Anyway, yeah, for a conjugate pair, Ka times Kb equals Kw. So Ka for ammonium times Kb for ammonia is equal to 1.0 times 10 to the negative 14. So I can say Ka of ammonium times Kb for ammonia, which we know from the previous problem is 1.8 times 10 to the negative 5, equals 1.0 times 10 to the negative 14 at room temperature. Okay, 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. That gives me 5.6 times 10 to the negative 10. Ka for ammonium is 5.6 times 10 to the negative 10. Okay, from there we can continue the rest of this problem. So let's go ahead and do that. So I can write I guess I'll just do it here. Equals x squared over 0.053 minus x. I'm going to assume that 0.053 minus x is approximately 0.053, given how small this Ka is. I mean, it's times 10 to the negative 10. It's incredibly small. X is probably not going to turn out that big anyway. So 0.053, subtracting a tiny x from it isn't really going to nudge the number all that much. But if I'm wrong, we can always test the assumption and see. So multiply by 0.053 and take the square root. 5.6 times 10 to the negative 10 multiplied by 0.053. I guess that would be 3.0 times 10 to the negative 11. So 3.0 times 10 to the negative 11 equals x squared. And take the square root. So square root of 3.0 times 10 to the negative 11 is going to be 5.5 times 10 to the negative 6. So I get x equals 5.5 times 10 to the negative 6 molar. And let's test our assumption. 0.053 minus 5.5 times 10 to the negative 6. This is on the order of 10 to the negative 3, right? It's 3 decimal places down. And this x is 6 decimal places down. So, yeah. If you're subtracting something that's 3 decimals away from the 3 in 0.053, it's not going to make a difference. It's going to be 0.052999, and eventually I guess you'll get a 4 and a 5. So, yeah, we were right to make this assumption. It saved us considerable time. And there we go. So x, that was the final concentration of ammonia, but more importantly, it was also equal to the final concentration of hydronium, which we can use to calculate pH. pH is just going to be negative log of 5.5 times 10 to the negative 6, which equals how much? If we've got 2 sig figs, we're going to need 2 decimal places in the end. Negative log 5.5 times 10 to the negative 6. That's going to be 5.26 if I round it to 2 decimal places. And there we go. Now, Ka times Kb equals Kw, I said. Why? Well, you might remember in the previous video, I went over the mathematics of equilibrium constants when combining multiple steps to get an overall reaction. So, let's be completely generic here and say I've got some weak acid HA, and I react it with water, and it dissociates, giving me A- plus hydronium. And let's say we do the reverse. Let's say we take this conjugate base now, A-, and put it in water. And that gives us HA plus hydroxide. Okay, the equilibrium constant for this is going to be Ka, which equals concentration of HA, or no, concentration of A-, I should say, times concentration of H3O plus over concentration of HA. And for this one, Kb equals concentration of HA times concentration of OH- over concentration of A-. And I forgot my minus. That's barely visible, but I'll count it. Okay. And if I add these chemical equations together, what do I get? HA cancels out with HA, A minus cancels out with A minus. I get 2H2O in equilibrium with hydronium plus hydroxide. Wait a minute. That's the auto-ionization of water. I know the equilibrium constant for this. It's Kw. Kw equals H3O plus times OH minus. And you might remember from the previous video, if I add two equations to get a third equation, then the equilibrium constant of the third equation equals the product of the equilibrium constants of the individual equations that were added. And even if you don't remember that, you can see it. If I multiply Ka times Kb, Ka times Kb equals concentration of A minus times concentration of hydronium over concentration of HA times concentration of HA, concentration of hydroxide, concentration of A minus. You can see that A minus cancels out with A minus, and HA cancels out with HA. And so all you're left with is hydronium times hydroxide, which is Kw. So yes, if they are a conjugate pair, Ka times Kb equals Kw. If it's not a conjugate pair, then of course it doesn't work. I can't use, for example, Ka for, I don't know, let's say hydrofluoric acid times Kb for ammonia. This doesn't work because hydrofluoric acid and ammonia are not conjugates of each other. It doesn't slide. So be careful about that. But otherwise, yes, Ka times Kb, if you're dealing with a conjugate pair, does multiply to Kw. And unless you're otherwise told, you can assume that Kw is just the room temperature value, 1.0 times 10 to the negative 14. All right. Now then, where do I want to go from here? I guess there's something else I should have calculated, which is the percent ionization or percent dissociation. Let's go ahead and do that for our two previous problems. First, let me define it. I guess I'll use light green, and yeah, I can fit it down here at the bottom. So percent dissociation or percent ionization. It's actually pretty intuitive when you think about it. Percent ionization equals essentially X over C times 100%, where X is the amount subtracted from the weak acid or base that's on the reactant side, and C is the starting concentration of that weak acid or base. Maybe it'll make more sense when we see examples. So the the percent ionization of ammonia in this example, what would it be? X is 5.2 times 10 to the negative 3 molar. And yeah, that's the amount that was subtracted from our 1.5 molar. So we can, I guess I'll write it up here. We can say percent ionization, I'll just abbreviate it percent ion, equals 5.2 times 10 to the negative 3 over, original concentration was 1.5 molar, times 100%. So then if I go ahead and crunch the numbers, 5.2 times 10 to the negative 3 over 1.5 times 100, the 100% is exact, that's going to be 0.34% equals 0.34% dissociated. Another way you can think about this, is what this is saying, if you remember from video number 11, I believe. In other words, this means that the Van't Hoff factor is 1.0034. If you remember Van't Hoff factors from a few videos ago, this translates to a Van't Hoff factor of 1.0034. You're probably not going to use the dissociation of weak acids and bases to calculate changes in boiling point and melting point for solutions, but in case you ever encounter that, here's how you would deal with it. It's pretty simple. Okay, let's calculate the percent ionization for this other example we did. So we had 0.053 was the original concentration, and we had x is 5.5 times 10 to the negative 6. So it's the 5.5 first. So 5.5 times 10 to the negative 6 divided by 0.053 times 100% gives me 0.010. 0.010. So percent ionization is 0.010%. Very, very low amount. So yeah, sometimes you'll have problems where you're actually given the percent ionization and asked to use that to calculate what the dissociation constant is. And those problems are usually way easier because, you don't have to deal with solving for a squared variable, especially not in the form of a quadratic equation. You'll be able to calculate x pretty easily if you have the percent ionization. We might see an example of that later. And if we don't see one in this video, then possibly in the next video. Oh yeah, we're not going to finish with acids and bases today. There's going to be more in the next video. I just kind of want to, I want to spread it out across 2 videos so that the math doesn't get too intense too quickly. And I just noticed a spot on my carpet that's gotten lighter. That's where the potassium hydroxide stuff got spilled. Great, I'll have to deal with that later. Neutralize it with vinegar or something. That'll probably make it worse. Anyway, what else do I have to talk about? Well, I guess we can talk about Ka and Kb values and how to just judge relative acid-base strength at a glance by looking at them. So if I go ahead and put this up in front of you, you can see that the higher the Ka value, the stronger the acid, the lower it is, the weaker, and same thing is true for Kb values. So high K values, stronger substances. So if I was comparing some weak acid to some other weak acid, not all weak acids are created equal. Same goes for bases. Just because they fall into the weak category doesn't mean they're all lumped into one level of strength. Even within the weak category, there is still some sort of pecking order, which is why sometimes they will refer to a weak acid as being strong, like I mentioned earlier, because what they mean when they say that is that it's strong in comparison to other weak acids. So when I say hydrofluoric acid is a strong acid, it's in the weak category, but it's stronger than, as you see in this visual, it's stronger than carbonic acid, it's stronger than hypochlorous acid, it's stronger than ammonium, it's stronger than the hydrogen phosphate ion, and of course it's stronger than water. But that shouldn't surprise anyone. So yeah, there you go. Even in the weak category of acids and bases, there are different levels of strength. Now, there is a relationship between the strength of a weak acid and its conjugate weak base. There is a relationship between those, and that's demonstrated right here. So basically, the stronger the acid, the weaker its conjugate base, and vice versa. This makes sense when you consider the formula we established a few minutes ago, Ka times Kb equals Kw. If Ka times Kb is a constant for for a conjugate pair, then that means the higher the Ka, the lower the Kb. And the higher the Kb, the lower the Ka. So if you've got a conjugate pair and their dissociation constants have to multiply to Kw, if one goes up, the other has to go down. So the really, really strong acids and bases, their conjugates are going to be extremely weak. You see at the top of the acid half of the chart, you see perchloric acid, sulfuric acid, hydroiodic acid. I don't know why they're just calling it hydrogen iodide, but I guess it's technically a correct name. Hydrobromic acid, hydrochloric acid. All of these are super, super strong acids, and of course their conjugates are going to be super, super weak bases. In fact, so weak that, like they say in the chart, they do not undergo base ionization in water. They can act as bases, but not in water. Maybe in some other solvent, but not water. And of course, the reverse is true for the strong bases. And, they haven't actually listed any of the super strong bases that we mentioned. What do they have there? The sulfide ion, I guess that counts as a really strong base. Probably not as strong as all those hydroxides we listed, but that's not really the important part to take away from here. The important part to take away from here is that for the extremely strong acids and the extremely strong bases, their conjugates are going to be so incredibly weak that in water, the reverse process just doesn't happen. And then for all those other acids and bases that are somewhere in that middle category, you do still see the relationship that the stronger the acid, the weaker the base, but because they're in that middle category, their conjugates are also going to fall into that middle category. Maybe it'll make more sense if I actually try to write it out here. So I guess over here I'll say increasing acid strength. Increasing acid strength. And I'm actually going to do something a little different from what they did. I'm going to have increasing base strength also going in the upward direction. Increasing base strength. Okay, so if I have a really, really strong acid, then its conjugate is going to be really, really weak. It's going to end up somewhere down here. Let's say that my really strong acids go from here to here. Then their conjugates are going to go from here to there. I guess that doesn't look exactly symmetrical, but just go with it. Okay, and then of course the really strong bases and their conjugates. The really strong bases are going to be in this top category. Their conjugates are going to be in the bottom category, like so. And then everything else, all of these kind of medium strength acids and bases, all of these medium strength acids and bases, their conjugates are also going to be in this medium range. So if I have something that's in here, for example, its conjugate still falls in that pink medium region. If I have something whose strength is up here, then it's going to have a conjugate that's also in this sort of medium strength. Of course, again, the relationship still holds that the stronger the acid, the weaker its conjugate base, and vice versa, but you can still expect if you start out somewhere in the middle, then your conjugate is also going to be somewhere in the middle. Maybe I rambled on a bit too long about that, but just wanted to try and drive that point home. The conjugate of a moderately weak acid is going to be a moderately weak base, and vice versa. The conjugate of a super strong acid is a super weak base, and vice versa. So most of the weak acids and bases we'll be talking about are going to fall into this middle category. Most of the weak acids we talk about, whenever we call them weak, we're referring to this middle block in here. You don't have to worry about the extremes. Okay, so that's relative acid and base strength. I guess we can talk about making predictions then. If we know about relative acid and base strength just based on dissociation constants, then we can actually make predictions about how a particular reaction will go. So, for example, if I react hydrofluoric acid with ammonia, forming the fluoride ion and the ammonium ion, is this equilibrium going to lie more to the right or to the left? And is the resulting solution going to be more basic or more acidic? Assuming it's at room temperature, do you expect the pH to be above 7 or below 7? Let me give you the dissociation constants. We already know for NH3, it's Kb equals 1.8 times 10 to the negative 5. As for hydrofluoric acid, that's 6.8 times 10 to the negative 4 for its Ka value. Okay, so the Ka for hydrofluoric acid is higher than the Kb for ammonia, so you would expect the hydrofluoric acid to be stronger of an acid than ammonia is as a base. So acid strength is greater than base strength. Overall, I would expect this solution to be more acidic. I would expect the pH to be below 7 at room temperature. I know I'm sounding like a broken record about this whole at room temperature thing, but mark my words, you will forget about the importance of it being at room temperature at the most inopportune time, and it'll probably cost you a whole lot of points, probably on one of those big standardized exams like the AP exam or the IB exam, or your final exam if you're in college. Well, I mean, AP and IB students still do, well, not all of them, but I think some of them still do get final exams from their teachers anyway. Okay, so let me see. Do I want to talk about it now, or should I save it for next time? I think I'll save it for next time. Predicting whether the reaction is going to move forward, or if it's going to, I shouldn't say move forward, if it's going to prefer products or reactants. You can actually tell by looking at the Ka values for the reactant acid and product acid, or by comparing the Kb values of the reactant base and product base. But I'll save that for next time. I don't want to make this too overwhelming. The super hard stuff is coming up in the next video, so I want you to have something digestible in this video. But I'll have to go back to that. I'll just have to remember to cover it in the next video. Let me make a note right now so I don't forget. Comparing those. Okay, now that I've noted it, I won't forget. Okay, well, I guess we've got 2 more things to consider. The acidity or basicity of salts, and then a brief discussion of the effective structure on acidity and or basicity. So the pH of a salt, predicting the acidity or basicity of salts. So I didn't find a problem for this topic under the under the chapter problems from the digital book, but that's okay because I've got 2 physical textbooks that I can use as problem sources. So here's one of the problems that my book lists. It says, predict whether aqueous solutions of the following compounds are acidic, basic, or neutral. So we've got ammonium bromide. We've got iron 3 chloride. We've got sodium carbonate. We've got potassium perchlorate. And we've got sodium hydrogen oxalate. Alright, so it's asking us to predict whether these are going to be acidic, basic, or neutral. So here's the general way to go about it. You just split it up into its component ions. So let's start with ammonium bromide. So you would split it up, you'd look at the ammonium and you would look at the bromide. And then you would ask yourself, well, does the bromide act as a proton acceptor? Does it react with water to form some hydrobromic acid plus OH minus? Well, no, we just talked about this. The bromide ion is the conjugate of one of your strong category acids. It's one of the super strong acids. Its conjugate is so weak that it cannot ionize in water. Or maybe ionize isn't the right word, but it can't accept protons from water. It's not strong enough to do that. So no, this doesn't happen. Therefore, there's no production of hydroxide due to the bromide being present. However, ammonium is one of those middle category acids, so it's going to be fine. It can react with water and form some ammonia plus, I guess, hydronium. So it will produce some hydronium, definitely a non-zero amount. Even if the equilibrium favors reactants, it's not going to have exactly 0 products. It has to have at least some products. So you are going to produce at least some hydronium, and you're not going to produce any hydroxide. So overall, if I put this stuff in water, I'm going to get something acidic, something with a pH below 7 at room temperature. Okay, let's move on to the next one, iron 3 chloride. So really, the test, without even having to write all this out, the test is to just look at each of them and look at their conjugates, basically. And if their conjugate is a strong acid or strong base, then they have no effect because they just don't produce anything. If you're the conjugate of a super strong acid or base, then you are a super weak conjugate base or conjugate acid. Not gonna make any hydroxide or hydronium. So yeah, looking at the chloride ion, chloride is the conjugate of hydrochloric acid, which is one of your strong acids, one of your really strong acids. Therefore, it's not going to dissociate with water. It's not going to produce any hydroxide. What about iron? So iron is going to be the conjugate of, I guess, iron hydroxide, FeOH3, or 2, depending on which version of iron. The point is, it can pluck some hydroxides out of the water. And if it does that, if it removes hydroxides from the water, then that leaves behind an H+, right? H2O minus a hydroxide leaves you with an H+. So effectively, this is producing hydrogen ions, which makes the solution more acidic. So this is going to be pH less than 7 as well, because iron hydroxide is not one of those strong hydroxides that dissociates readily. The strong hydroxides are all of group 1 and about half of group 2, but none of the transition metals. Okay, sodium carbonate. So sodium would be the conjugate of sodium hydroxide. And I guess when I say conjugate, I'm not referring to the one proton difference conjugates that we've been looking at for most of this video. Sorry if I wasn't clear about that. But yeah, if I imagine adding hydroxide to sodium, sodium hydroxide is one of my strong bases. Even if you could turn it into sodium hydroxide, it would split back up into sodium ions and hydroxide ions anyway. So sodium, no effect. What about carbonate? If I add hydrogen to the carbonate, I get carbonic acid, which is a weak acid. It's not going to fully dissociate back into hydrogen ions and carbonate ions. Therefore, the carbonate, it has some basicity to it that sticks. It can remove some hydrogen from the water permanently, leaving behind hydroxide. This is a basic solution, pH greater than 7. Okay, potassium perchlorate. Potassium hydroxide is a strong base, so the potassium isn't going to be taking any hydroxides out of the water, not permanently anyway. If it does, it'll form a strong base that dissociates back anyway. What about adding hydrogen to the perchlorate ion? That would give you perchloric acid, which is a strong acid, so it's not going to stick. If you form HClO4, it'll split back up into H+ and ClO4-. So this is going to be neutral, pH equals 7. Okay, what about sodium hydrogen oxalate? Sodium hydroxide is a strong base, so sodium has no effect. Add a hydrogen to the hydrogen oxalate ion, and that would give you oxalic acid, which is not one of our strong acids, so the removal of hydrogen from the water has some permanence to it. This is going to be a basic solution, pH greater than 7. Now, some of you might be asking, well, how do I know that it's going to accept protons rather than donate them? How do I know that it's going to accept protons rather than donate them? How do I know that Hc2O4, when given the opportunity to interact with water, how do I know that it goes this way, forming H2C2O4 plus OH-? I guess I should use double arrows there, versus this way, where it loses another hydrogen and forms C2O4 2-, and Oh, and I forgot to put the minus sign there. C2O4 minus plus hydronium. How do I know that it's going to do this and not this? Well, it actually can do both, but this is the only one that matters. This is the only one that matters. It turns out that successive dissociations become harder and harder. So if I have H2C2O4 and I dissociate it, I'm just going to skip over the plus H2O just to save time. And you make this. Okay, so that's the first acid dissociation. That's going to be Ka1, I will call it. Ka1 for oxalic acid. The second Ka, where you lose the second proton, or Ka2. Ka2 is going to be significantly smaller than Ka1. In fact, we see something similar with sulfuric acid. The first proton of sulfuric acid, we said, is strongly acidic. You lose it pretty much effortlessly. The second proton is harder to lose. Why? One intuitive idea I can give you that can help explain this is, as you remove protons, the charge of the rest of the molecule or ion becomes more negative. And the more negative it is, the harder it is for positive charge to go away from it. Negatives attract positives, after all. So how easily can you lose a positive hydrogen ion from a polyatomic ion that's negative overall? Having that negative charge kind of helps pull back any hydrogen ions that are trying to escape. Some manage to escape eventually, but it's harder. Less of them can pull it off the more negative the charge is. So that's a simple, intuitive explanation for why successive dissociation constants are lower. So you can expect that the Ka for this process, which is Ka2, is going to be really low in comparison to the let's see, in comparison to the oh, we've got quite the predicament here, because we're comparing the Ka of the second step to the Kb of the first step. I believe the Kb of the first step would still be higher. Can I prove that mathematically, though? I imagine I could, but I'd have to tinker with it. And yeah, doing it live probably isn't the best idea. Let me actually look up what the dissociation constant for oxalic acid is. Let's see, so so for oxalic acid, Ka1 is 5.9 times 10 to the negative 2. And Ka2 is 6.4 times 10 to the negative 5. So going in the opposite direction, if you take the hydrogen oxalate ion with water and you go this way, you go back to forming oxalic acid, the dissociation constant for that would be Ka1 times Kb equals Kw. So yeah, that's going to be on the order of 10 to the negative 11, I think. 1.0 times 10 to the negative 14 over 5.9 times 10 to the negative 2 is going to be 1.7 times 10 to the negative 13. Kb for this process is 1.7 times 10 to the negative 13, while Ka for this process is Ka2, 6.4 times 10 to the negative 5. Okay, so actually it is going to be this process. Okay, never mind. It's going to be a pH less than 7. That kind of feels unfair, because the way the problem was written, I wasn't expecting to have to look up Ka values to figure this out. I'll look over this again later, and if I have more to say about it, I'll mention it in a pinned comment. Almost dropped my calculator there. Okay, where do I want to go next? So, right, one last topic, and then we'll look at some more problems before we wrap things up. The relative, or the effect of structure on acidity. Okay, so there is a pattern that you can observe. If you ask me, it's not a very strong pattern, but it's a pattern nonetheless. You can take advantage of it, but it does have some exceptions. I don't think it's a very reliable pattern, but that's just my opinion. So, as you can see in that diagram, it appears to be the case that the further you go down and right, the stronger the substance, the more the substance acts as an acid, and the more strongly it does so. And if you go in the opposite direction, if you go up and left, then you get increasing base strength and decreasing acid strength. So, as for the reasons behind this, you'll get to explore that a lot in organic chemistry, if you ever take the organic chemistry course. But I'll give you a little idea of what's going on. So, comparing HF with HCl, for example. Comparing HF with HCl. So, HCl is the stronger acid, and what makes it the stronger acid is that, well, the chloride ion is the weaker base, right? The stronger the acid, the weaker its conjugate base. So, what makes a very good conjugate base? One that doesn't actively seek to steal more hydrogens away from the neighboring water molecules. Why is it that chloride is happy not bothering the neighboring water molecules? Well, because in spite of its negative charge, which you would think makes it seek out protons, its negative charge is distributed over a large volume. The chloride ion is much bigger than the fluoride ion, and I'll try to draw the fluoride smaller to emphasize that. Chloride is much bigger than fluoride, so that negative charge is more spread out, so it's kind of more stable. Whereas the fluoride ion, when it's alone, the negative charge is concentrated in a really small space. So its ability to attract positive charge, to try and pluck off protons from nearby water molecules is going to be greater. So yeah, there's some attraction that forms between the fluoride ions and the hydrogens of nearby water molecules that doesn't seem to happen with chloride. And it's, how do I say it? It's not the most reliable pattern, but it kind of makes sense. It kind of makes sense, but personally, I don't fully buy it. It's just, there's so many other things to consider, and actually, this other thing that we need to consider, if we go back to the chart, and we compare two things that are in the same row. So let's compare water with hydrofluoric acid. Let's compare water with hydrofluoric acid. It turns out that hydrofluoric acid is the stronger acid when compared to water. And there's a reason for this. The reason has to do with the difference in electronegativity. So fluorine is more electronegative than oxygen, which means it does a better job of pulling the electron density away from hydrogen. It does a better job of pulling electron density away from hydrogen when compared to how oxygen performs. So since fluorine is better at pulling away the electron density, this hydrogen is more positive. So there's more positive charge concentrated on this hydrogen, which makes it more attracted to the negative charge of some base. Let's say you had some hydroxide floating around, or even some water. Well, maybe water isn't. Yeah, let's just go with water. See, the problem is these two factors kind of conflict with each other. I think you can see that. And this is why I don't really like this attempt at explaining acid and base strength based on structure. It just feels like you've got rules that fly in the face of each other, and there's nothing that's really telling you which rule is more important. And if you try to make predictions based off of this, you'll make incorrect predictions so often that it doesn't feel like there really is a pattern. But that's what chemists do. They try to insist that patterns exist when they don't. What was I trying to draw here? Oh, right. So since a lot of electron density is being pulled away from this hydrogen by the fluorine, it makes this hydrogen it turns it into a location where a lot of positive charge is concentrated, which makes it more attracted to negative charge, say from the lone pair of the oxygen of a nearby water molecule. So a connection between these two guys can form more easily because of that. And there you go. Those are the two basic rules that quote unquote rules that we can, what's the word I'm looking for? The rules that seem to be at play, judging by the two patterns that we see across this chart. The vertical pattern and the horizontal pattern for acids and bases in the same column, or acids and bases in the same row. So yeah, real messy stuff. In the same vein, there's There's a special category of acids that we call oxyacids. Basically, they're acids that have a lot of oxygen in their Lewis structure. And for this, there's actually a pretty strong pattern. It turns out that the more oxygens you have in the structure, the stronger the acid. The more oxygens in the structure, the stronger the acid is. And I guess this ties into something called inductive effects, which you'll learn about some more if you ever take organic chemistry. But it's kind of the same thing as why hydrofluoric acid is a stronger acid than water. It's because of the electronegativity. Having lots of high electronegativity oxygens in there, all pulling electron density away from the hydrogen, making them more positive, or maybe just pulling the electron density away so much that there's practically no bond there. I guess that's another way you can think about it. When the hydrogen is next to something with a really high electronegativity, it's practically already an ionic bond and not so covalent anymore. It's teetering on the edge of being covalent. And there we have it. So the rest of this video is just going to be looking at problems. So let's go ahead and look at some. Where did we leave off? Of course, we'll skip anything that we've already done examples of, or anything that's easy enough that I think you should be able to handle them on your own. You know the deal by now. 26. Explain why the neutralization reaction of a strong acid and a weak base gives a weakly acidic solution. Oh, this is something we didn't talk about. Okay. So, strong acid, weak base. Let's say, for example, hydrochloric acid with ammonia. Okay, so a strong acid has to dissociate completely. So, single arrow. If a strong acid or strong base is involved on the reactant side, no equilibrium arrows, it's just a single arrow. So HCl plus NH3 gives you NH4 plus Cl minus. Now this is happening in a solution, so there's water around. So while the chloride doesn't go back and turn into HCl, the ammonium can interact with the water. So the ammonium that you've now made can go back and interact with the water and form some ammonia plus hydronium ion. And since some hydronium ion is formed, overall you're going to get an acidic solution. And of course, the more intuitive way to predict it, if it's a strong acid versus a weak base, acid strength overcomes base strength, so more acidic, less basic, acidic overall. I think that's pretty obvious to a lot of you guys, but you know, there's an actual explanation for why you get an acidic solution. It's a two-step process. Okay, 27, basically the same thing, but in reverse. Weak acid with strong base. I think from number 26 you get the idea, so I'll let you tinker with that on your own. 28, use the list of important industrial compounds to answer the following questions regarding each of those compounds. Identify the strong Bronsted-Lowry acids and strong Bronsted-Lowry bases. Okay, so using that chart, yeah, I'll skip that. 29. The odor of vinegar is due to the presence of acetic acid. List in order of descending concentration all of the ionic and molecular species present in a 1 molar aqueous solution of this acid. Okay, I mean, that's not that hard. Acetic acid is a weak acid. It's going to reach some sort of equilibrium. It's not going to dissociate completely. And dissociation constants tend to be small. They tend to favor reactants. You're not going to get much product. So the original acid is going to be at a high concentration. It's not going to decrease in concentration all that much. And the acetate ion and hydrogen ion that result from its dissociation are both going to be at equal concentrations to each other, but still much lower than the 1 molar starting concentration of the acetic acid. Okay, number 30. I'm guessing it's the same thing. Yeah. 31. Explain why the ionization constant for sulfuric acid is larger than the ionization constant for sulfurous acid. Okay, so these are oxyacids, more oxygen, more inductive effects, more withdrawn electron density away from the hydrogens, making them more positive, making it easier for them to separate from the rest of the structure, from the rest of the molecule. Yeah, we just talked about that. 32, explain why the ionization constant for hydroiodic acid is larger than for hydrofluoric acid. Because of size, the iodide ion is going to be more stable because it's just bigger. It can spread out its negative charge over a greater volume, so the tendency to be attracted to or to have positive charge attracted to it is just going to be lower. Really messy stuff. I don't like this whole attempt at, well, I've already made my statement about this stuff, so let me just move on without rambling. 33. Gastric juice, the digestive fluid produced in the stomach, contains hydrochloric acid. Okay. Write a complete balanced equation for the neutralization reaction. We can skip that. That's stuff that you've been able to do since probably 10 videos ago. 34, same thing. We know how to write chemical equations. Let's move on. What is the ionization constant at 25 degrees Celsius for the weak acid CH3NH3 plus? I think that's methylammonium. The conjugate acid of the weak base, methylamine. Yeah, that's what it is. It's methylammonium and methylamine. So they want the Ka, and they've given you the Kb of the conjugate. Kw equals Ka times Kb for conjugate pairs. We've seen examples of that. Moving on. 36, same thing, we'll skip. 37, which base, methylamine or dimethylamine, is the stronger base? And which conjugate acid, methylammonium or dimethylammonium or methylammonium, is the stronger acid? You'll learn how to name these, by the way, when you do organic chemistry. We'll do that in video number 19. Well, maybe not these examples specifically, but Actually, let me talk about these for a bit. Let me talk about those for a bit. So, there's a couple of organic ions and molecules here that are pretty similar to ammonia and ammonium. So the structure of ammonia is this right here. You've seen it enough times, I would think you have it memorized by now. And ammonium ion is going to look like this. It's going to be a tetrahedral shape. So this is a weak base, this is a weak acid, and I've had students who are given problems where they're given something like CH3NH2 and they don't know whether it's an acid or a base, and there's actually an easy way to tell. If you think of CH3NH2 starting from NH3, start with NH3, but replace one of the hydrogens with a CH3. That is, replace it with a carbon attached to 3 hydrogens. There you go. A single carbon with 3 hydrogens attached to it is called a methyl group. So this is called methylamine. This is called methylamine. So basically the nitrogen there with hydrogens and carbons attached to it, it's called an amine group. It's got a methyl group attached to it, so it's a methylamine. And if it had 2 of these methyl groups, it would be called a dimethylamine. And if all 3 of the hydrogens were replaced with CH3s, it would be called a trimethylamine. Naming rules aren't really what I'm trying to get at here, but just FYI. Okay, so you should expect this to continue functioning as a base because you still have that lone pair on the nitrogen that can pluck off a hydrogen from water and form this. And it's going to have, of course, a positive 1 charge. And yeah, just, replace these other hydrogens with CH3s, or sometimes you have to replace it with a C2H5. A C2H5 would look like this. This is what's called an ethyl group, for those who want to know what it's called. And yeah, if you attach this to the nitrogen, and of course it's still going to have 2 hydrogens attached to it, then yeah, these all fall into the same category. These are all bases, because at the end of the day, the main feature that makes it a base is the nitrogen with the lone pair. And these are all acids because, well, their main feature is the nitrogen that's fully substituted. Fully substituted probably doesn't mean anything to you guys right now since we haven't done organic chemistry. What's another term or phrase I could use here aside from fully substituted? It's got no lone pairs on it. It's fully connected, I guess you could say. Has the maximum number of bonds it can handle. Has no lone pairs. And has an excess positive charge. Okay, so there's your side note about those ammonia-like and ammonium-like compounds or polyatomic ions. So, yeah, back to 37. Which base methylamine or dimethylamine is the stronger base, and which conjugate acid is the stronger acid? Well, let me take a look at the numbers first to get an idea. Okay, this is rather interesting. So, dimethylamine and ethylamine are both stronger than ammonia as bases. That's according to my data table. And you would think this means that the more methyl groups that you use to replace hydrogens in the ammonia, you would think that adding the methyl groups makes it more acidic, but the dimethylamine is actually weaker than... Oh, wait, no, I'm looking at the wrong one. I was looking at dimethylamine and ethylamine, my bad. Dimethylamine 5.4 times 10 to the negative 4. Methylamine 4.4 times 10 to the negative 4. Okay, yeah, so the more methyl groups, the stronger it is as a base. Okay. And why would that be the case? Well, if I can't easily explain why it would be a stronger base, maybe it's better to argue why its conjugate would be a stronger acid. Or a more stable acid, I should say. A weaker acid. I'm tripping over my words today. So, adding a methyl group increases acid strength, which means it increases base strength, which means it decreases conjugate acid strength, which means the conjugate acid is more stable. So this is more stable than this. And I guess it's because it just becomes a bigger molecule and there's more room to spread the charge around. I mean, I'm tempted to use an argument from organic chemistry here, but that wouldn't be fair since you guys haven't taken the organic chemistry course. More carbons around the location where the charge occurs tends to increase the stability of the charge, but that's not something you're expected to know. So yeah, I would just argue on the basis of size. You're probably not going to be asked about this anyway. But yeah, for our purposes, let's just argue on the basis of size. A bigger molecule has more room to spread the charge around, which makes it more stable, which lowers its tendency to seek out the opposite charge, which makes this a weaker acid, which makes its conjugate a stronger base. So the more methyl groups you add, the stronger the base. And so dimethylamine is going to be the stronger base, and dimethylammonium is going to be the weaker acid. So the CH3,2NH is the stronger base, and the CH3,2NH2 plus is the weaker acid. Okay, 38, which is stronger, NH4 plus or HBRO. Oh goodness. Let's see, so nitrogen versus bromine. Well, HBRO, that's an oxyacid, and oxyacids are typically strong, so I think that's what they're getting at. I was never asked to make these sorts of comparisons in AP chemistry, so don't worry too much about this. It's just the writers of this book really, really care about this idea of structure determining acid strength. Number 40, predict which acid... Yeah, I'm skipping 39, by the way. 40, predict which acid in each of the following pairs is the stronger and explain your reasoning. Yeah, I think we've done enough of that. Let's move on to the next set. Making predictions based on structure is something better reserved for when you take Organic Chemistry 1 in college. Oh yeah, they teach it in the first semester of college organic chemistry. It's probably something you'll see in the third or fourth week. But at least by then you'll have enough chemistry experience under your belt that you can make the arguments a little more coherently. 41. Predict which... Okay, so same as 40. 42. Rank the compounds in each of the following groups in order of increasing acidity or basicity as indicated and explain the order you assign. I guess it's more like 41 and the others. Just follow the pattern that I showed in, let's see. Follow this pattern for those past 2 or 3 problems. This is what they want you to do. Just look at the periodic table, look at what the hydrogens are being paired with, and the further down and to the right, the more acidic. And the further up and to the left, the more basic. 43 looks like same-o. Okay, next set. Both hydrofluoric acid and hydrocyanic acid ionize in water to a limited extent. Which of the conjugate bases is the stronger base? Okay, so again, they want you to make the prediction based on the pattern on the periodic table. Skip. 45, let's see. List in order of descending concentration all the ionic and molecular species present. We did something like that. Skip. 46, are the concentrations of hydronium and hydroxide in a solution of an acid or a base in water directly proportional or inversely proportional? Explain your answer. They're inversely proportional. We talked about this. If the concentration of one goes up, the concentration of the other goes down. After all, their product has to be a constant. The only way for one to go up is for the other to go down. 47. What 2 common assumptions can simplify calculation of equilibrium concentrations in a solution of a weak acid or base? Well, one of them is the assumption that X is negligible in comparison to the starting concentration. I don't know what the other common assumption is that they're referring to, so I can't really comment on that. Let me try and think for a second. A common assumption when working with acid or base dissociations. Oh, I think I know what it is. For polyprotic acids and bases, usually the second dissociation is going to be so much lower in terms of its K value in comparison to the first dissociation that it doesn't yield much extra hydronium or hydroxide. Okay, let's actually talk about that. Let me show an example. Let's use phosphoric acid as our example. Phosphoric acid. So phosphoric acid, H3PO4, dissociates, and yeah, I'm skipping the water and just writing hydrogen ion plus dihydrogen phosphate ion. So that has a first dissociation constant, Ka1, equals 7.5 times 10 to the negative 3. Then the next dissociation, you've got H2PO4 minus, gives you another H plus HPO4 2 minus. And that has a Ka2 of 6.2 times 10 to the negative 8. And I guess I'll list the third one. HPO4 minus dissociating into H plus and PO4. Oh, wait, that's a 2 minus. And PO4 3 minus. And that's got Ka3 equals 4.2 times 10 to the negative 13. Really weak stuff. So, if you start with, I don't know, let's say you start with 1.2 molar of phosphoric acid. Okay, you lose X here. You started with 0 here and here and gained X. And so in step 1, if we do the calculation, can we get away with assuming that the X is negligible here? Let's see, if I do X squared over 1.2 equals Ka1, then 1.2 times 7.5 times 10 to the negative 3, if I take the square root of that, that's 9.5 times 10 to the negative 2, which is significant. Okay, quadratic formula. Quadratic formula it is. Okay, 7.5 times 10 to the negative 3 times 1.2 minus x equals x squared. Distribute the 7.5. 7.5 times 1.2, what did that give us? That gave us 9.0 times 10 to the negative 3. And then minus 7.5 times 10 to the negative 3x, and that equals x squared. Move everything over to the right, and we get 0 equals x squared plus 7.5 times 10 to the negative 3x minus 9.0 times 10 to the negative 3. Quadratic formula, so that's going to be negative 7.5 times 10 to the negative 3 plus or minus the square root of 7.5 times 10 to the negative 3 squared minus 4 times 1 times negative 9.0 times 10 to the negative 3 all over 2 times 1. So in one case I get 9.1 times 10 to the negative 2, and in the minus case I get a negative, which is impossible. So yeah, it's 9.1 times 10 to the negative 2. X equals 9.1 times 10 to the negative 2 molar. Okay, so now if you were asked to calculate something like the hydrogen concentration or even the pH, you could stop right here because there's a big enough gap between these Ka values that you know you're not going to get much hydrogen out of here, out of this second step. First, because it's a smaller Ka value, but there's another reason why you're not going to get much yield for the second step. And that is because you already have hydrogen present for the second step. It's the hydrogen that you made in the first step. So we've got, how much hydrogen did we make? 9.1 times 10 to the negative 2 molar. And let's see, here you've got 9.1 times 10 to the negative 2 molar of your dihydrogen phosphate ion that was produced in the first step. So if I try to subtract, let's call it y, if I subtract y there and add y here and add y here, that started at 0, so yeah, minus y plus y plus y. Okay, so if I were to try writing the equilibrium expression here, then I'd have Ka2, which is 6.2 times 10 to the negative 8, equals, I'll just write it as Ka2, equals 9.1 times 10 to the negative 2 plus y, 9.1 times 10 to the negative 2 plus, there's not enough space here. Where should I write it? I guess over here seems good. Ka2 equals 9.1 times 10 to the negative 2 plus y times y over 9.1 times 10 to the negative 2 minus y. Okay, well, it turns out, and you can predict this pretty reasonably from both the starting concentration and the Ka2 value. If you do the 5% test, you'll see that the y is negligible in comparison to 9.1 times 10 to the negative 2, which means subtracting it from 9.1 times 10 to the negative 2 doesn't decrease the value noticeably, and adding it to 9.1 times 10 to the negative 2 doesn't increase the value noticeably. So 9.1 times 10 to the negative 2 plus y is essentially still 9.1 times 10 to the negative 2. Same thing if you minus y. So these approximately cancel out, and you get y equals a measly 6.2 times 10 to the negative 8. And yeah, if you add that to 9.1 times 10 to the negative 2, you're practically adding nothing. So you can stop after the first step. If the successive Ka values aren't too different from each other, then you will want to be careful and try and carry out the second step. But a lot of times, successive Ka values are far enough apart that the extra yield of hydrogen or hydronium or hydroxide from the second step doesn't add much on to what you got from the first step. So a lot of times the first step is all you need to figure out the final hydrogen, hydronium, hydroxide concentration. Okay, which problem were we looking at there? I've lost my place. Oh, right, we were asking about, it was 47, what two common assumptions? So I think that's the second common assumption they're referring to, is that you can treat the equilibrium concentration of hydrogen, hydronium, or hydroxide for a multi-step process as just being the result that you get from the first step most of the time. At least I think that's what they're hinting at. Otherwise, I have no idea what they're talking about with the second common assumption. 48. Which of the following will increase the percent of ammonia that is converted to the ammonium ion in water? Okay, so Le Chatelier, basically. Yeah. If ammonia gives you NH4 plus and OH minus, then adding sodium hydroxide is adding more product, which shifts equilibrium to the left, so that's a no. Adding hydrochloric acid, yes, that will have the effect of neutralizing some of the hydroxide on the product side, which will drive the reaction to the right. And addition of ammonium chloride. Well, it would shift equilibrium further to the right, but would it increase the percent dissociation? Because you're increasing the concentration of the ammonium too. Let's see, it would increase the denominator, and if the denominator is large enough, then the numerator can creep up without affecting the ratio all that significantly. Okay, yeah. Adding NH4Cl. I'm overthinking it. Yeah, it'll drive the reaction further to the right, so the percent ammonia. Oh, wait. We're not adding more ammonia, we're adding more ammonium. Okay, that would drive the equilibrium to the left. My bad, I misread. And I shouldn't have. Ammonia itself can't be paired with chloride. This is a sign that we need to wrap up the video as soon as possible. I'll try not to rush things, though. Okay, so yeah, just some Le Chatelier there. 49 looks like the same. What is the effect on the concentrations of those substances when the following are added to a solution of potassium nitrite in water? Okay, so more Le Chatelier. Potassium nitrite is effectively just the nitrite ion. The potassium is just going to be a spectator ion. So, yeah, the equation that you're looking at is NO2 minus plus water gives HNO2 plus OH minus. And from there it's Le Chatelier. 51, same idea, different reaction. 52, why is the hydronium ion concentration in a solution that is 0.10 molar in HCl and 0.10 molar in HCOOH? Methanoic acid? Yeah. And 0.10 molar in methanoic acid determined by the concentration of HCl. Kind of for the same reason that I just mentioned with the second dissociation of phosphoric acid, actually. The HCl dissociates completely. The HCl dissociates completely. So HCl gives what did they say? 0.10 molar of hydrogen ion. Okay, And if you've got 0.10 molar of hydrogen ion already, and then you add a weak acid to it, then for HCOOH, methanoic acid, in order for it to dissociate and produce more H+, let's see, and I guess that would be HCOO minus. In order for this dissociation to happen, it's not going to proceed to the right as much because there's already some hydrogen ion present. So this starts at 0.10 and you subtract x. This starts at 0.10 and you add x. And this starts at 0 and you add x. And yeah. So it's kind of like what happened in the second step here. You already had some hydrogen present, which I'm at a loss for words. How do I say this? You already had some hydrogen present here, which made it harder to proceed forward because you only need a really tiny amount of additional product in order to reach this Ka value. You just need to be a little more than 0. The only reason it proceeds forward at all is because it has to be more than 0, but it's not going to proceed forward all that much. You're not going to get a lot of product to begin with because the Ka value is so small. If you already have a head start on how many products you have, then you don't need to add much more. So yeah, same kind of ordeal going on here. We'll talk about this some more in the next video. This is something that we call the common ion effect. We'll dig deeper into it in the next video. But having some product already present reduces the rate of product production, basically. And some of you might be wondering, well, how do I know that the HCl was added first? How do I know that we had 0.10 molar of hydrogen first before the dissociation of methanoic acid started? It doesn't matter. It doesn't matter which order you mix them in. It doesn't matter if the HCl went in first or if the methanoic acid went in first, or if they both went into the solution and got mixed at the same time. You'll reach the same end point. So it's simpler to think of it as the strong acid going in first. It just makes it easier to do calculations and think about the problem. But if you want to think about it in the reverse order, okay, you put it in and you establish some sort of equilibrium, right? Then, once equilibrium is reached, you apply a stress. You add HCl. What does that do? Well, it increases the hydrogen ion concentration. You've increased the concentration of products, which will shift the equilibrium to the left. So you end up in the same place, and that place is very, very low dissociation of methanoic acid. Already low because it's a weak acid and its K value is small, and even lower due to the presence of excess product. All right, so that was 52. So you can assume that the methanoic acid doesn't produce enough additional hydronium or hydrogen to matter. Therefore, you can just use the amount that you get out of the HCl, and that'll be approximately the correct value. 53. From the equilibrium concentrations given, calculate Ka for each of the weak acids and Kb for each of the weak bases. Okay, so they gave you the equilibrium concentrations. All you have to do is plug in the numbers. That's easy enough. We did that in the previous video, so we'll skip. I mean, when I skip these, I'm hoping that for the relevant problems anyway, that you guys are still practicing them on your own. I'm skipping them just because I don't want to bore you with something you already know how to do. But you should still practice even if you know how to do it, because when you don't practice, you suddenly forget how to do it at the most inopportune time. And we all know what that's like. Or am I the only one that's been in that sort of scenario? I don't think so. 54, same as 53. 55, determine Kb for the nitrite ion. Ah, here we go. This is what I was talking about earlier. I knew we would get a problem like this, or at least I was hoping. Determine Kb for the nitrite ion in a 0.10 molar solution. This base is 0.0015% ionized. And 56, I think I prefer 56 just because I don't have to write as many zeros. Let's do 56. So it says determine Ka for hydrogen sulfate ion in a 0.10 molar solution. The acid is 29% ionized, which is actually pretty good. Okay, so we've got HSO4 minus, so its starting concentration is 0.10 molar. And, okay, I'll write the water this time. I've been skipping on the water for the past few equations. HSO4 minus plus H2O gives you sulfate plus hydronium. Okay, don't care about the amount of water. This starts at 0, increases by x. This starts at 0, increases by x. This starts at 0.10, decreases by x. Well, this time we can actually calculate x right away because we know the percent ionization. We know that x over c times 100% is equal to 29%. So we can say x over 0.10 molar is the starting concentration, equals 29 over 100, which is 0.29. 0.29 times 0.10 is 0.029, so x equals 0.029. And now that we have that, we can calculate Ka very easily. Ka equals x times x, so 0.029 squared. Over 0.10 minus 0.029. And if I do that subtraction, that's going to be 0.07. That's going to be 0.07. Rounding to 2 decimal places, of course. And yeah, 0.029 squared. What is my calculator doing? 0.029 squared is about 8.4 times 10 to the negative 4, and 8.4 times 10 to the negative 4 divided by 0.7 is 1.2 times 10 to the negative 3, which I guess just rounds to 1 times 10 to the negative 3 because we only get 1 sig fig out of that. I think I mentioned in either the previous video or the video before it that this is the point in the course where the sig fig rules start to get really, what's the word I'm looking for? They start to give us results that don't seem reasonable. And the temptation to ignore the sig fig rules grows and grows, and you'll even see the teachers stop deducting points for ignoring the sig fig rules. As long as you don't use an unreasonable amount of extra sig figs. But yeah, there's that problem. And you can do 55 on your own now that you've seen 56. Maybe some of you could do it on your own before even seeing 56. Okay, so that's that sheet. A few more to go before we wrap things up. Calculate the ionization constant for each of the following acids or bases from the ionization constant of its conjugate base or conjugate acid. So in this one, they expect you to look up the Ka or Kb values. But yeah, we know how to do this. Ka times Kb for conjugate pairs equals Kw. 58 looks like pretty much the same thing, so we'll skip. 60, calculate the concentration of all solute species in each of the following solutions of acids or bases. Assume that the ionization of water can be neglected. And oh, that's probably the second assumption. That must be it. That's the second assumption they were talking about in, I think it was like problem 47. That must be it. Assume that the self-ionization of water contributes little to nothing to the hydronium or hydroxide produced. Okay, that must be it. Anyway, calculate the concentrations of all species. So basically set up your ice tables, find the final concentrations, and if you need to use the quadratic formula, use it. We've been through this. We've seen examples of that in this video, and we've seen just general ice table problems in the previous video. 61, propionic acid, or as I prefer to call it, propanoic acid, that's the official name, is used in the manufacture of calcium propanoate. That's the official name, not propionate, or however it's pronounced. A food preservative. What is the pH of a 0.698 molar solution? Okay, ice table. C equals 0.698. Decreases by X. The propanoate ion and the hydronium ion increase from 0. They each increase by X. Been there, done that. White vinegar is 5% by mass solution of acetic acid in water. If the density of white vinegar is 1.007 grams per cubic centimeter, what is the pH? Okay, so you would assume you've got 1 cubic centimeter, and that would mean you've got 1.007 grams of white vinegar. And 5% of that is acetic acid, and the rest is H2O. So whatever 5% of 1.007 grams is, that's your grams of acetic acid. Use the molar mass of acetic acid to get the moles of acetic acid. Divide it by the volume. 1 cubic centimeter is 1 milliliter, so convert the milliliters to liters, and yeah, you'd have the moles of acetic acid, you'd have the volume of the solution, you'd have the concentration. And if you've got the concentration and you look up the Ka value for acetic acid, then all that's left is to set up an ice table and calculate the concentration of hydrogen or hydronium, take the negative log, and you've got the pH. I think you've seen enough between this video and the relevant previous videos that you should be able to do that on your own. 63. Let's see. If 20 grams of lactic acid is used to make a solution with a volume of 1 liter, what is the concentration of hydronium ion in the solution? Take the grams, convert to moles. Take the moles over the 1 liter to get molarity, and same as 62. Ice table, calculate final concentrations. Look up the... Actually, no, they gave you the Ka value in this problem. Didn't they? Yeah, they did. Okay, 64. So, it's a base that will accept 2 protons. It's a diprotic base. Kb1 is 7 times 10 to the negative 7. Kb2 is 1.4 times 10 to the negative 11. That's 10,000 times smaller. So, like with my phosphoric acid example, you can probably ignore the second step and just base your calculations on the first step. Actually, no, you can't ignore the second step entirely, because they want the concentration of each species, which means that you also need to calculate the final concentration of the other product of the second step. So yeah, just because of what they're asking for, you'd have to actually go through both steps. But it's not too bad, because based on what we saw with the phosphoric acid example, the concentration of the other product from the second step is just going to be equal to the second K value, right? These were approximately the same, so they canceled out, leaving y equals Ka2. In the case of this problem, you're just going to get y equals Kb2. Okay, that's not that horrible. And then for your hydroxide concentration, just use whatever you get from the first step. And for your whatever the conjugate acid of nicotine is, whatever the first conjugate acid is, just use the concentration you get for it from the first step as well. Okay, 65, we've got the pH of some solution is 1.92. Determine Ka from this data. Not that hard. Use the pH to calculate the hydronium concentration. 10 to the negative pH gives you hydronium. You've got the starting concentration of the HF. The hydronium concentration is basically going to be the X. Okay, let me at least set it up. It's probably better to show it rather than tell. So we've got the pH is 1.92. So let's write the reaction. HF plus water gives fluoride plus hydronium. And yeah, so this starts at, they said 0.23. Yeah, it starts at 0.23, decreases by x. These each start at 0, increase by x. And so their final concentrations are going to be X and X. But we can calculate X because X is the hydronium concentration. X equals the hydronium concentration equals 10 to the negative whatever the pH was. And yeah, from there you've got X. You can calculate Ka because it's just going to be X times X, X squared over 0.23 minus X. Yeah, so find X, and then find 0.23 minus X, whatever it is, plug it into the denominator, and plug your X squared into the numerator, and you're done. Okay, and 66 looks like it does the same thing. 67 seems to be the same as well. 68, also the same. So yeah, all four of those problems work out pretty much the same way. Just be careful with your pH versus pOH values. If you're dealing with a base and you calculate 10 to the negative pH, that's your hydronium concentration. And if hydronium is not in your reaction, if your reaction involves hydroxide, you better be careful. But outside of that, there's not much to those. Okay. 2 more sheets to go. 69. Determine whether aqueous solutions of the following salts are acidic, basic, or neutral. Oh, well, we already did that. I didn't think they had them in this book. Well, we already did an example like that earlier, so you know the gist of it. Looking at 69D, CH3, NH3Br. CH3NH3, that's one of those ammonium-like compounds. It looks like ammonium, except replace one of the hydrogens with a methyl group. So that's just a little hint for 69D. But otherwise, you know how to deal with these. 71, Novocaine. Let's see, ionization constant given. Is the solution acidic or basic? Oh, because it's a salt of procaine and hydrochloric acid. Okay, well. Oh, I see. They give the ionization constant, but they don't tell you if it's acid ionization or base ionization. But that's okay, because you know that the chloride is the conjugate of HCl. It's the conjugate of some acid. So the rest of that molecule is probably the conjugate of some base. So yeah, it's a base dissociation constant. It must be. Or is it? Hold on. So you mix procaine with hydrochloric acid and you get that. But removing the chloride ion from it, yeah, I'm not too sure about this one because what's troubling me is if you remove the chloride ion and you get C13H21O2N2 plus, is that procaine, or is procaine some neutral compound that's, I guess, one hydrogen less than that? I guess that's the part that's bothering me. Because if procaine is actually C13H20O2N2, then that would mean that the ionization constant they've given you is for its conjugate, and you would have to do Kw divided by that to get the appropriate constant. I don't know. Maybe I'm overthinking this. But I guess if I were you, I would just go to Wikipedia or something and look up procaine versus novocaine and make sure of which one is which. But I would expect that this would be an acidic solution overall. I would think that C13H21O2N2 plus, because it's got that positive charge, it's probably not going to be a proton acceptor, because positively charged polyatomic ions will repel other positive charges typically. So I think it's more likely to lose protons than gain them. So I'm going to argue it's acidic based on that. But yeah, you might want to go to Wikipedia and double check procaine versus novocaine just to be on the safe side. And then they ask, what are the hydronium and hydroxide concentrations and the pH of a 2% solution by mass of novocaine? We already did a problem that was worded similarly, where they gave you the percent by mass and the density. I think instead of grams per milliliter, they gave it as grams per cubic centimeter, which is the same thing, but you know how to deal with this one. Just go back to that previous example, or the previous problem that we did. Well, I didn't do it, but you know, the one that I described how to do, in case you've forgotten what to do. Okay, polyprotic acids, 72. Which of the following concentrations would be practically equal in a calculation of the equilibrium concentrations in a 0.134 molar solution of carbonic acid, a diprotic acid, hydronium concentration, hydroxide concentration, carbonic acid concentration, bicarbonate concentration, or carbonate concentration? The products of the first step would be practically equal. So that would be the hydronium ion and the bicarbonate ion. Those would be practically equal because in the second step, very little of the bicarbonate will dissociate into additional hydronium and carbonate ion. And as for hydroxide isn't even in any of the steps. It's going to be inversely proportional to the hydronium ion concentration. And I guess I'll pull up the phosphoric acid example again, just to kind of clarify. So yeah, these are going to be practically equal, the products of the first step, because this product, it'll decrease, but only by a really, really tiny amount, and this product will increase, but only by a really, really tiny amount. So their final concentrations will be practically equal even though not exactly equal. 73, calculate the concentration of each species present in a 0.050 molar solution of hydrosulfuric acid. Okay, so two-step process, look up the Ka1 and Ka2 values, and you should be good to go. It's not too different from the phosphoric acid example or other polyprotic examples that we have seen. And I think we've got, yeah, this is the last set. Is there anything here that needs our attention? Calculate the concentration of each species present in a solution of phthalic acid. And they've given us the two steps. Let's see. Ka2 appears to be 1,000 times smaller, on the order of 1,000 times smaller than Ka1, which I think is a big enough gap that the second step isn't going to contribute that much additional hydronium. But they do want the concentration of each species. That's how they make you do the second step. Because without doing the second step, there's no way to get the concentration of the second product, the one that's either gained or lost the second hydrogen. That's how they get you. 75. I don't even know if I want to read that. Okay, I'll read through it real quick. Okay. So, description of salicylic acid. That's the stuff in aspirin, by the way. Both functional groups of salicylic acid ionize in water. What is the pH of a saturated solution of the acid? And the solubility is 1.8 grams per liter. Oh. In that case, no, the solubility, that's just giving you the initial concentration. I thought for a minute that they were actually giving you the concentrations of the post-dissociation products, but no. Use the solubility to calculate the initial concentration. Assume you've got 1 liter, and then take 1.8 grams of salicylic acid, divide by its molar mass. Good luck calculating that. And yeah, just do the 2 separate steps. Actually, no. If they just want the pH, do the first step. Just use Ka1 1.0 times 10 to the negative 3 and calculate the hydronium from that step. The other step, don't even bother. 4.2 times 10 to the negative 13. That's on the order of 10 billion times smaller. That's not going to get you any additional hydronium. Don't even bother. Part B, aspirin was discovered as a result of efforts to produce a derivative of salicylic acid that would not be irritating to the stomach lining. Okay, is it going to be more of the same? The CO2H functional group is still present. I mean, now you're getting into organic chemistry language, and that's too much for them to expect of you at this point, but if you can understand it, you can attempt Part B. Yeah, I would pass on Part B. It doesn't seem all that fair. It's throwing too much stuff at you. For someone at this point in the course, it just feels too overwhelming. 76, the ion HTE-, and I guess Te is tellurium, is an amphiprotic species. It can act as either an acid or a base. What is Ka for the acid reaction of HTE minus? What is Kb for the reaction in which HTE minus functions as a base in water? They expect us to just figure that out. How? Are they really just making parts A and B an exercise in looking up values in a data table? That kind of feels, what's the word, insulting to the student's intelligence. Wow. That's another problem where I would not want to meet the person who wrote them. I think that's happened twice now. Just two problems that are written so poorly that if I ever met the person who wrote them, I don't know what I'd do. Okay, what about part C? Demonstrate whether or not the second ionization of H2TE, I guess, dihydrogen telluride, can be neglected in the calculation of the concentration of HTE minus in a 0.10 molar solution of H2TE. Oh, yeah, so sometimes the successive Ka values are close enough that you do actually have to include the second step when calculating the hydronium or hydroxide concentration. But in most cases, like with our phosphoric acid example, or part A of problem 75, the difference between Ka1 and Ka2 is so huge that you can skip on step 2 if all you're looking for is the pH or the hydronium hydroxide concentration. I said hydronium and hydroxide like I was naming a compound. The hydronium or hydroxide concentration. But yeah, so you just have to look up the dissociation constants for those. And I actually don't have them listed in my table, so I guess you'll just have to Google them or something. Or maybe your book has a bigger data table. But yeah, it's nothing too new. Nothing all that new at all. You'd have to look up the Ka1 and the Ka2 values for part C. Parts A and B, you just have to look up the values, which doesn't feel like a real problem. So yeah, I guess that's where we're going to end things for tonight. So plan for next time, we're going to look at the common ion effect, which I mentioned earlier. It'll be the first thing we do next time, is talk about the common ion effect. And we'll dig deeper into acids and bases. We'll look at acid-base titrations involving weak acids and weak bases, because those are not so simple. The equivalence point for them is not going to be at a pH of 7. And yeah, we'll talk about the notion of buffered solutions. We'll also talk about the dissociation of salts. Weak acids and weak bases are not the only weak electrolytes. There are also a lot of salts that have really, really low solubilities. The equilibrium for those salts is something we'll study in the next video. And then that'll be it for equilibrium, at least in terms of dealing with chemical equations. It'll still be involved in the next thing we cover, which is thermodynamics. But yeah, that's what we're going to be covering next time, so make sure you understand this stuff, make sure you have mastered your 5% rule, or your assume X is negligible rule, however you want to do it. I prefer the assume X is negligible process, assume and then check. But if you like the 5% rule and it works well enough for you, then feel free to use it. I can't stop you, as much as I'd like to. Anything else I need to say before wrapping things up? I can't really think of anything, but you know the drill. If I remember something that I need to add, you'll see it in a pinned comment, so definitely do check the comment section for stuff like that. Anyway, this has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I'll see you in the next video.